explosions will expel much of this material into intergalactic space. The activity of the central black hole may also play a role, heating the surrounding gas and preventing it from collapsing into new stars. If no fresh gas flows in, the system will gradually enter a passive state where star birth ceases. The black hole at the galaxy's core is a key factor in determining its future. If it continues to consume matter, it may become even more active, releasing powerful jets of energy, creating shock waves that alter the surroundings. Such processes can ease star formation or suppress it. If the surrounding gas is black hole will enter a dormant state and only faint traces of X-ray. This system does not exist in isolation. Galaxies orbit around it, ability that they will collide. A merger could trigger a burst of star formation, but it could also destroy the ordered structure of the spiral arms, transforming the system into an elliptical form. Such events often lead to chaos in the internal dynamics of stellar orbits and fundamental changes in morphology. If this formation becomes part of a larger galactic cluster, the pressure from the surrounding environment may strip it of its remaining gas, completely shutting down star formation. In that case, it will become a fainter and more passive system where stars age without new generations replacing them. Observations suggest that this stellar island is surrounded by a vast dark matter halo. This invisible substance holds the galaxy together, preventing its stars from drifting apart. The question of how dark matter is distributed and what properties it possesses remains one of the greatest mysteries in modern astrophysics. Some theories suggest that dark matter consists of dense clumps, influencing the motion of stars and gas. Other hypotheses propose that dark matter interacts with itself in ways that we have yet to detect. Over time, the galaxy will become dominated by stars that have reached the end of their life cycles. White dwarfs, neutron stars, and black holes will gradually replace the younger, more luminous stars. If star formation ceases entirely, this world will, in trillions of years, become a place populated only by the faint remnants of once bright celestial bodies. Beyond internal factors, the system's fate will also be shaped by the evolution of the universe itself. The expansion of space is gradually increasing the distances between galaxies. If this process continues, then in the far future, surrounding objects may disappear beyond the cosmic event horizon, leaving this stellar world in complete isolation. The question of whether this galaxy could ever become home to intelligent life remains unanswered. If life arises within one of its planetary systems, it will encounter conditions different from those found in our own galaxy. In an era when bright stars fade, civilizations may search for ways to harness the energy of white dwarfs, neutron stars, or even black holes. Perhaps, in the distant future, advanced technologies will emerge that allow civilizations to manage energy resources on a galactic scale. This stellar world is one of countless objects in the universe, each a dynamic system evolving over time. Its fate could take many paths, retaining its current structure, transforming into an elliptical system, merging with other formations, or becoming isolated due to the expansion of the universe. But no matter what its final destiny may be, it remains part of the continuous cosmic process. Every star, every gas cloud, every gravitational force is a link in the great chain of the universe's evolution. We've only begun to worry, and many discoveries still lie ahead. As observers continue to study distant galaxies, each new detail becomes part of an endless exploration that will never truly end. As time passes, This vast galactic structure will continue to change, shaped by both internal and external cosmic forces. While the present era is marked by active star formation, powerful stellar winds, and dynamic interactions, the distant future will bring a more gradual transformation. The balance between creation and destruction, between the birth of new stars and the fading of the old, will ultimately determine how this system evolves over billions or even trillions of years. The slow depletion of gas will lead to a decline in the birth of bright, massive stars. The spiral arms, once vibrant with nebulae and young stellar clusters, will begin to fade as fewer new stars form to replace. The remaining gas will become increasingly diffuse, spread thinly across the galaxy, no longer able to collapse into dense clouds that fuel star formation. If no external gas flows in from intergalactic space, it will slowly transition into a quietive state. While the visible structure of the galaxy undergoes these changes, its invisible dark matter halo will continue to play a crucial role in its long-term evolution. The unseen gravitational framework, stars and gas together, future mergers, interactions, and even the galaxy's eventual fate. Some theories suggest that dark matter halos are not steady, they evolve over time, possibly affecting how galaxies like this one maintain their structure over cosmic timescales. As the number of new stars decreases, the stellar remnants will grow. White dwarfs will become the dominant stellar type, their faint glow persisting as they gradually cool over trillions. Neutron stars and black holes will also become more common, remnants of stars that once illuminated the galaxy. If enough black holes exist within the system, they may act gravitationally, forming dense clusters or even merging into larger structures that fall toward the central supermassive black hole. Over billions of years, the galaxy will undergo a transformation driven by gravitational interactions with other systems. If it merges with a neighboring galaxy, it may lose its spiral structure, becoming an elliptical system where stars move in more randomized orbits. Such a transition would mark a major shift in its evolutionary path, reshaping the way stars and stellar remnants are distributed throughout its volume. In a more scenario, if the galaxy is absorbed into a massive galactic cluster, it may experience what is known as ram pressure stripping. This process occurs when a galaxy moves through the hot gas that fills the space between galaxies in a cluster. The pressure exerted by this intergalactic medium can strip away any remaining gas, effectively halting star formation entirely. This would leave behind a system composed mostly of aging stars, gradually fading over time. Beyond these local events, the larger-scale universe itself will influence the ultimate fate of this galactic giant. The expanse, driven by dark energy, is accelerating. If this acceleration continues indefinitely, galaxies will become increasingly isolated, drifting apart until they can no longer interact with one another. Over time, this system may find itself alone in an expanding void, with no nearby galaxies left to merge with or draw gas from. In the far future, as the last remaining stars exhaust their nuclear fuel, the galaxy will enter its final stage. White dwarfs will continue to cool, becoming black dwarfs, cold, dark remnants emitting no light. Black holes will persist, slowly evaporating through Hawking radiation, though this process takes an unimaginably long time. Over an almost inconceivable timescale, the galaxy itself may become a vast, dark collection of degenerate matter, silent and unchanging. But even in this distant future, the story of this galaxy will not truly be over. The fundamental forces that shaped it, dark matter, cosmic expansion, will continue to operate. New discoveries may one day reveal unknown processes that influence its fate in ways we cannot yet predict. Perhaps advanced civilizations, if they arise and endure, will find ways to manipulate stellar remnants, harnessing the energy of neutron stars or even black holes to sustain life long after ordinary stars have burned out. For now, this galaxy remains a vibrant and active system, a luminous beacon in the cosmos. Its arms swirl with gas and dust, its stars shine brightly, and its core harbors the powerful force of a supermassive black hole. It is a system still in motion, still evolving, still participating in the grand, ongoing story of the universe. And as we continue to observe it, to study its mysteries and map its future, we are reminded that the universe itself is not static. Every galaxy, every star, every atom is part of an endless cosmic dance, a process of change and transformation that spans across time and space. This galaxy's story is far from over. It is just one chapter in the ever-unfolding narrative of the cosmos, a reminder that, in the vastness of the universe, there is always more to discover. As the cosmic clock continues to advance, the evolution of this galactic titan will be shaped by forces both predictable and mysterious. While the structure we observe today is vibrant and full of energy, the deeper laws governing the universe ensure that no celestial body remains unchanged. Over unimaginable timescales, this stellar system will transition through different phases, each marking a new chapter in its vast history. The present moment, defined by the ongoing formation of stars, will eventually give way to a quieter era. The great nebulae that now serve as stellar nurseries will slowly disperse, leaving behind only the stars that have already formed. Without a steady influx of cold gas, no new generations will emerge to replace those that burn out. This decline will be gradual at first, barely perceptible over human lifetimes, but over billions of years, the difference will become clear. The galaxy's arms will fade, the glow of massive blue stars will disappear, and only long-lived red dwarfs and cooling remnants will remain. While the visible features of the galaxy change, unseen processes will continue to influence its fate. The dark matter halo surrounding the system will persist as a gravitational scaffold, shaping the movement of its stars even after the loss of its brightest members. Some theories suggest that interactions within dark matter halos could lead to subtle, long-term effects on galactic evolution, possibly altering the way stars orbit or influencing future mergers in ways not yet fully understood. Even as the galaxy settles into a more passive state, the remnants of its former brilliance will still be present. White dwarfs will form a vast population, each a dimming ember of a once luminous star. Neutron stars, the collapsed cores of the most massive stars, will rotate silently, some still emitting faint pulses of radiation. Black holes, formed from the deaths of the heaviest stars, will drift through the system, invisible but ever-present, exerting their gravitational influence. The central supermassive black hole, now dormant or only occasionally active, will remain as the galaxy's silent core. Over time, it may continue to gain mass through slow accretion or by merging with other black holes, should galactic interactions bring new material into its reach. If the system experiences a major black hole could awaken once more, unleashing powerful jets of energy that briefly reshape its surroundings before fading into darkness again. The long-term fate of the galaxy is also bound to the broader evolution of the universe itself. If cosmic expansion continues at its current accelerating rate, galaxies will drift further apart, severing their connections to the larger structures they once belonged to. Eventually, even the faintest traces of other galaxies will recede beyond the observable horizon, leaving this system alone in an increasingly empty cosmos. Without new interactions to provide fresh material, it will continue its slow transition into darkness. In the deepest future, when trillions of years have passed, even the longest-lived stars will begin to fade. Red dwarfs, which burn their fuel with extreme efficiency, will eventually exhaust their reserves, leaving behind a universe filled only with cooling remnants. The galaxy will become a place of silent white dwarfs, non-rotating neutron stars, and black holes, drifting endlessly through the void. Even these objects, given enough time, may meet their end. White dwarfs will cool to black dwarfs, emitting no heat or light. Black holes, the most enduring structures of all, may slowly evaporate through the slow process of Hawking radiation, vanishing into the vacuum of space. Yet despite this seemingly inevitable decline, the universe remains a place of possibility. If advanced civilizations arise within the galaxy's lifespan, they may develop ways to harness the energy of its remnants, finding new methods of survival long after the stars have faded. Technologies beyond our current imagination may allow life to persist, adapting to the cold, dark universe that will one day emerge. For now, however, this galaxy remains alive, its stars burning brightly, its spiral arms stretching across space, its black hole holding court at the center of a vast and complex system. It is a place of ongoing transformation, where cosmic forces play out on scales both vast and intricate. Every supernova, every drifting planet, every magnetic field tells a story written in the language of the cosmos. As we continue to study it, we are reminded that the universe itself is never static. It is an ever-changing tapestry of matter, energy, and space-time, each moment leading to the next in an infinite sequence of events. This galaxy's journey is far from over, it is simply part of the grand, continuous motion of the cosmos. And as long as there are observers to look toward the stars, its story will continue to unfold, written across the fabric of time itself. The journey of this galaxy through the cosmic expanse continues, an unceasing progression through the vast, uncharted reaches of time. While its present form is defined by swirling arms of stars, luminous nebulae, and a dynamic interplay of stellar forces, the distant future will see it undergo transformations that stretch beyond the scope of current understanding. Each stage in its evolution is part of a grander cycle, where birth, growth, and decay are inextricably linked. Even as the light of new stars fades, the underlying gravitational structures will endure. The stars that once illuminated the galaxy will drift through a steadily dimming sky, bound to their orbits by the unseen mass of dark matter. Over eons, these orbits may shift due to subtle gravitational interactions, causing some stars to migrate outward while others spiral inward toward the central black hole. In some regions, dense stellar remnants may cluster, forming compact systems of white dwarfs, neutron stars, and black holes locked in a slow gravitational dance. While large-scale interactions will become increasingly rare as the universe expands, this does not mean the galaxy will remain entirely isolated from cosmic events. Rogue objects, free-floating planets, interstellar debris, or even intergalactic stars ejected from distant collisions, may pass through its boundaries, altering local dynamics in unexpected ways. Occasionally, binary systems may undergo disruptions, fling outward at immense speeds while the other falls into the depths of a black hole. These rare events will provide brief but dramatic moments in an otherwise long, gradual shift toward equilibrium. At the heart of it all, the central black hole will persist as the galaxy's gravitational anchor, long after its brightest stars have faded. If no further matter is available to feed it, it may remain dormant, a dark monolith at the center of a dying system. Yet in the event of a galactic merger, even in the distant future, it could awaken once more, consuming stellar material and releasing vast amounts of energy in a final display of activity before the universe grows too empty to sustain such processes. On the longest timescales, when even the most enduring stars have faded into obscurity, the galaxy will be reduced to a vast collection of stellar remnants. White dwarfs, once the glowing cores of sun-like stars, will cool until they no longer emit any heat or light. Neutron stars, relics of past supernovae, will persist as silent, invisible spheres of dense matter. Black holes, the ultimate endpoints of stellar collapse, will remain scattered across the galactic remnant, their presence detectable only through their gravitational influence. Yet even black holes are not eternal. The slow process of Hawking radiation, a quantum effect predicted by theoretical physics, will cause them to lose mass over unimaginable timescales. As the final stages of the universe unfold, these black holes will gradually evaporate, releasing their remaining energy into the darkness. Eventually, after a period so long it defies human comprehension, the last traces of what was once a grand and thriving galaxy will dissipate, leaving behind nothing but the vast, empty expanse of space. But even in this apparent finality, the story of the universe itself may not be over. Some theories suggest that new physical processes could emerge in the distant future, leading to the birth of entirely new structures, new galaxies, or even new forms of matter and energy. The eventual fate of the cosmos remains one of the greatest mysteries, one that extends beyond even the long arc of this galaxy's existence. For now, this stellar system remains an active, vibrant participant in the ongoing story of the cosmos. Its stars still shine, its nebulae still swirl with potential, and its future remains unwritten. Whether it eventually fades into isolation, merges with another galactic system, or becomes the cradle of new cosmic phenomena, it is a reminder that the universe is not static, it is an ever-changing expanse of creation, transformation, and mystery. The galaxy's journey, like the universe itself, is one of constant motion. And as long as observers exist to study it, to trace its evolution, and to uncover the forces that shape it, its story will continue, woven into the grand tapestry of existence, a testament to the boundless nature of the cosmos. The passage of time within this galaxy, like that of all cosmic structures, is dictated by forces both seen and unseen. For now, it remains a place of light, energy, and movement, a system still brimming with stellar activity in the subtle interplay of gravity, radiation, and magnetic fields. Yet the deeper laws of physics ensure that change is inevitable. The stars that shine today will one day burn out, their remnants drifting through space, forming the silent foundation of a future where darkness and cold dominate. Even in the near future, on a galactic scale, this system will begin to experience noticeable shifts. The rate of new star formation will decline as available gas reservoirs dwindle, and stellar winds, supernovae, and active galactic feedback continue to expel material into intergalactic space. The most massive stars, those that once defined the brilliance of the galaxy's spiral arms, will be the first to vanish, leaving behind a less dynamic but still evolving stellar population. As the era of new stars comes to a close, the dominant sources of energy within the galaxy will change. While today it is driven by the nuclear fusion of young, luminous stars, in the future, much of its energy output will come from compact remnants, white dwarfs, neutron stars, and black holes. These objects, relics of past stellar generations, will continue to interact in gravitationally complex ways, forming dense stellar clusters where unusual astrophysical phenomena may emerge. With no new material to sustain star formation, the galaxy will enter a state of slow structural decay. The spiral arms, once teeming with brilliant clusters of hot, young stars, will become more diffuse and less distinct. The central regions, dominated by older stars, will gradually take on a more elliptical shape, as stellar orbits become increasingly randomized due to long-term gravitational interactions. If the system does not experience another major merger, it may retain much of its spiral character for an extended period, but eventually, it will lose the energy that sustains its grand structure. The presence of dark matter, though invisible, will continue to shape the motion of stars and stellar remnants. This unseen mass, concentrated in a vast halo extending far beyond the visible edges of the galaxy, ensure that its overall gravitational integrity remains intact, even as individual stars come and go. Yet as time stretches onward, the exact nature of dark matter's influence remains uncertain. If dark matter interacts with itself or decays over cosmological timescales, it could subtly alter the galaxy's evolution in ways not yet fully understood. Far in the future, black holes will become the dominant gravitational players within the system. The central supermassive black hole, now a relatively quiet presence, may awaken if a late-stage galactic collision provides it with new material to consume. However, if no such event occurs, it will continue to exist in relative dormancy, exerting its pull on the remaining stars and stellar corpses that orbit its dark center. Meanwhile, smaller black holes, formed from the collapse of once massive stars, will roam the galaxy, occasionally merging and releasing bursts of gravitational waves that ripple through the fabric of spacetime. The next phase in the galaxy is dominated by slow stellar dimming and cooling. The white dwarfs left behind by sun-like stars will take trillions of years to cool to black dwarfs, their faint infrared glow gradually fading into total darkness. The neutron stars, though more stable, will also lose energy over immense timescales, their once powerful magnetic fields dissipating until they become featureless, dense remnants. In the most distant future, when even these last stellar remnants have faded, the galaxy will be reduced to a vast, dark cloud of compact objects. White dwarfs will have long since cooled beyond detectability, neutron stars will have settled into silent motion, and the remaining black holes will be the only significant sources of gravitational influence. The occasional gravitational interactions between these objects may eject some of them into intergalactic space, while others may slowly spiral inward toward the supermassive black hole at the center. Even black holes are not eternal. If the theories of Hawking radiation hold true, over an unimaginable number of years, they evaporate, emitting minuscule amounts of radiation until they finally vanish. In the final stages, the last remaining structures of the galaxy will disappear entirely, leaving nothing but the expanding void. Yet even in this apparent finality, the larger fate of the universe remains unknown. Some cosmological theories suggest that new physics could emerge at extreme timescales, allowing for the rebirth of matter, the formation of new energy structures, or even the possibility of an entirely new phase of existence. Other models suggest that the universe will continue expanding indefinitely, growing colder and more desolate as entropy reaches its maximum. But for now, this galaxy is still very much alive. It is a place where stars are born and die, where black holes lurk in the shadows, and where gas clouds drift between the stars, waiting to be pulled together into new systems. It is still undergoing change, still writing its story in the language of light and gravity. And as long as there are eyes to observe it, whether human or some other intelligence that may one day rise within its countless stars, its journey through time will remain an inspiration. It is a reminder that the universe is not a static void but an evolving, dynamic entity, filled with forces beyond our comprehension, shaping worlds beyond our reach. This galaxy's tale is far from over. It is but one part of a far greater cosmic narrative, one that stretches across the depths of space and the boundless reaches of time. And as long as the universe itself exists, the echoes of its existence, its transformations, and its mysteries will endure, woven into the grand and infinite fabric of the cosmos. The journey of this galaxy is a testament to the ever-changing nature of the cosmos, where time, gravity, and energy weave an unbroken narrative of transformation. Even as it moves toward a quieter, less dynamic state, the fundamental forces that shaped it continue to operate, ensuring that its evolution, though gradual, will never truly cease. As the last great bursts of star formation fade, the galaxy will settle into a state of equilibrium, where the remaining stars age and cool without the replenishment of new stellar generations. The once vibrant interplay between young blue giants and glowing nebulae will be replaced by an increasing dominance of red and orange stars, those that burn their fuel slowly and persist long after the more massive stars have perished. Over time, even these long-lived dwarfs will begin to disappear, leaving behind a sky populated mostly by stellar remnants, silent echoes of a once thriving system. Though large-scale star formation will have ceased, cosmic interactions will continue on smaller scales. Gravitational encounters between stellar remnants may lead to occasional mergers, where white dwarfs collide to produce faint, short-lived bursts of energy. Some neutron stars, locked in decaying orbits around one another, may spiral inward over the course of eons, unleashing powerful gravitational waves in their final moments before merging into a single, ultra-dense object. These events, though rare, will be among the last luminous displays in the galaxy's history, marking the remnants of processes that once fueled its brilliance. At the heart of the system, the supermassive black hole will remain the most dominant force, exerting its influence over whatever matter still orbits its deep gravitational well. If no new gas is available for accretion, it will exist in a state of quiet solitude, an immense but invisible presence that once governed the flow of material at the galactic core. However, should future interactions send new objects to whether wandering stars, smaller black holes, or the remnants of galactic mergers, it may still flare to life in brief, final outbursts of radiation before returning to dormancy. Beyond the slow transfer in the galaxy itself, the broader cosmic landscape will undergo equally profound shifts. The expansion of the universe, driven by dark energy, will continue stretching the fabric of space, increasing the distances between galaxies. If current models hold true, this system will one day be so far removed from its nearest neighbors that no light from them will ever reach it again. It will exist in solitude, drifting in an ever-expanding void, separated from any potential sources of new energy or interaction. In this distant future, even the most enduring stars will fade. The red dwarfs, which burn their hydrogen reserves with remarkable efficiency, will eventually deplete their fuel, transitioning into dim, cooling husks. White dwarfs, scattered throughout the galaxy, will continue their slow cooling process, radiating away of heat until they become black dwarfs, invisible and undetectable, existing only as faint gravitational imprints in the darkness. The galaxy, once a brilliant collection of spiraling stars and nebulae, will become a quiet graveyard of matter, a system of dead star holes, and unseen remnants, orbiting in patterns set but no longer changing. The gravitational pull that once held it together will remain, but without active energy sources, it will simply persist as a vast structure of cold, inactive bound no longer formations. But even these lingering remnants will not endure forever. If Hawking radiation is correct, then over unimaginable spans of time, even the black holes that dominate the galaxy's final phase will slowly evaporate, radiating away their mass particle by particle until nothing remains. The last trace of structure within this system, indeed, within any system, will be erased as even these cosmic titans fade into nothingness. At this stage, the universe itself may have reached what is theorized as the heat death, a state where entropy has maximized, all available energy has been evenly distributed, and no further work can be done. The last remaining particles will drift aimlessly in a sea of darkness, with no stars to shine, no forces to bind them together, and no structure left to shape the cosmos. And yet, even in this seemingly final state, mysteries remain. Some theories propose that at extreme timescales, new physics may emerge, allowing for the spontaneous formation of quantum fluctuations that could give rise to entirely new structures, perhaps even a new universe. Others suggest that unknown forces, beyond current understanding, could initiate a cosmic rebirth, resetting the universe into a new cycle of expansion, contraction, and formation. For now, however, this galaxy remains a place of light, energy, and motion. It is still home to stars, to planetary systems, and to forces that shape the cosmos on scales both vast and intricate. It is still evolving, still transforming, still existing as part of the grand, ever-unfolding story of the universe. And as long as there are minds to observe it, whether human or some future intelligence that may one day rise within its stars, its journey will not be forgotten. It will stand as a testament to the vastness of time, the relentless power of cosmic forces, and the mystery of existence itself. Even in the face of inevitable entropy, even in the depths of the farthest future, the legacy of this galaxy, its cycles of formation, its celestial dance, its silent end, will remain woven into the fabric of the cosmos, a whisper in the endless symphony of space and time. Even as the inevitable march of entropy dictates the distant fate of this galaxy, its existence, past, present, and future, remains a crucial part of the larger cosmic narrative. While its stars will one day fade, while its spiral arms will dissolve into a formless collection of stellar remnants and its black holes will eventually disappear, it is not a mere passive participant in this grand story. Every collision, every burst of star formation, every gravitational interaction it has ever undergone has contributed to shaping the vast, evolving tapestry of the universe itself. For now, it is still a place of motion, where stars drift along their ancient orbits, where remnants of once massive suns cool in the silence of space, and where the invisible forces of dark matter still hold it together. The fabric of spacetime bends subtly around its remaining black holes, the last gravitational wells marking where brilliant clusters of stars once illuminated the cosmic night. Even as star formation ceases, interactions between stellar remnants will continue. Binary white dwarfs may occasionally merge, igniting in final supernovae that momentarily rekindle some of the brightness lost over eons. Some neutron stars may collide, releasing bursts of gamma radiation that flash across space before vanishing into the abyss. These events will become rarer and rarer as time stretches forward, their light appearing like distant echoes of an era that once flourished. If a cosmic traveler, a future intelligence from a civilization born on one of this galaxy's planets, were to witness its slow transformation, they would see it as a system settling into a quiet, eternal slumber. The intricate balance of forces that once gave rise to its grand structure will dissolve, leaving behind a ghost of what once was. The beautiful, swirling motion of its spiral arms will be nothing but a memory written in the positions of long-cooled stellar remnants, their orbits preserving the shape of the past long after the light has faded. And yet, even in this state of near total stillness, the galaxy will continue to move. It will drift through the expanding universe, carrying with it the remnants of countless past generations of stars, planets, and possibly even life that once arose in its systems. Every star that has ever shone, every world that has ever formed, every cosmic event that has ever unfolded within its boundaries has left a mark upon the larger fabric of reality. But what lies beyond the end? Some theories suggest that as the expansion of the universe accelerates, structures like this galaxy will become increasingly isolated, eventually disappearing beyond the event horizons of one another. This would mean that, in the deepest future, nothing from the outside universe would be able to reach this lone stellar graveyard. It would exist in complete solitude, no longer connected to the broader cosmic web from which it once drew its material and energy. Yet other possibilities remain open. There are theories that hint at the idea of cosmic rebirth, suggesting that fundamental forces may shift over unimaginable timescales, triggering a new phase of universal evolution. Perhaps the very fabric of space-time will undergo a transformation, giving rise to new structures, new energies, or even entirely new forms of matter. Could something rise from the ashes of this long silent galaxy, reshaping its cold remnants into the seeds of another universe? Or perhaps, if there is intelligence capable of enduring across such timescales, this galaxy may not remain a passive relic of the past but instead a domain of cosmic engineering. If civilizations survive the death of their stars, could they find ways to reignite new suns? Could they harness the gravitational energy of black holes to create new sources of warmth and light? Could they defy the seemingly inevitable fate of entropy, bending the rules of nature to construct a new age of stellar activity? For now, such questions remain beyond our reach. What is certain, however, is that the universe is not a static entity, nor has it ever been. From the moment of its birth, it has been in constant flux, each stage leading into the next, each transition reshaping the fate of galaxies, stars, and worlds. This galaxy's story, though it may seem to end in silence, is not a tragedy. It is a story of cycles, transformations, and endurance. It is a reminder that even in the face of entropy, in the face of an ever-expanding cosmos, there is meaning in the motions of celestial bodies, in the interactions of cosmic forces, in the rise and fall of stellar systems. It is not just a fading structure in an ancient universe, it is a link in a chain that stretches from the distant past into the unknowable future. It is a testament to the grand forces that govern reality, a cosmic echo that will resonate across time. And as long as there are observers, whether human or otherwise, to look toward the stars, to seek understanding, to marvel at the scale of existence, then the story of this galaxy will never truly be over. It will live on in the minds that remember it, in the equations that describe it, and in the unbroken continuum of the universe itself, a whisper in the void, a trace in the infinite, a mark upon eternity. Even in the farthest reaches of time, when the last embers of this galaxy have faded and its structure has dissolved into the silent drift of stellar remnants, its existence will remain woven into the fabric of the universe. The forces that shaped it, the stars that once illuminated its spiral arms, and the events that unfolded the expanse have left an imprint upon reality itself. Though no longer a place of brilliant star clusters and luminous nebulae, it will not be forgotten by the cosmos. The energy that once flowed through its stars has been dispersed, the elements forged in their nuclear furnaces scattered across the void, now part of an unseen legacy stretching far beyond its borders. The gravitational ripples from ancient collisions still echo through spacetime, faint but real, inscribed into the very structure of the universe. In a universe where time stretches infinitely forward, the galaxy's past is not erased but absorbed into the grand continuity of existence. Every burst of stellar radiation, every gravitational interaction, every moment of transformation has contributed to shaping the cosmos as it is now, and as it will be in the future. Yet if the universe itself has an ultimate fate, if the expansion continues to accelerate, or if new physics emerges beyond our understanding, then even the idea of permanence may be an illusion. If dark energy persists, this galaxy will be carried ever outward, away from all others, lost in a cold and empty expanse where no new interactions can take place. In such a future, its remnants will continue their endless drift, untouched, unseen, unknowable to anything that might still exist elsewhere. The universe is cyclic. If there is a deeper pattern beyond the present expansion, then perhaps this is not the true end. Some theories suggest that the cosmos may one day contract, reversing its expansion and pulling everything back toward a new singularity, a rebirth where all past matter and energy are reshaped into the foundation of a new reality. If such a fate awaits, then this galaxy, though long dissolved, may become part of the material that fuels the birth of new stars, new galaxies, new structures beyond imagining. And even if the cosmos remains in perpetual expansion, with entropy driving it toward darkness, there may yet be unseen forces at play. Perhaps deep in the void, unknown mechanisms could reignite cosmic processes, birthing new structures in ways we cannot yet comprehend. Could remnants of this galaxy, scattered and cold, find new purpose in an epoch where the laws of physics themselves change? If intelligence endures, if civilizations, whether from this galaxy or another, find ways to persist beyond the deaths of their stars, then the knowledge of what once was will not vanish. Records of this galaxy's past may be preserved, its structure mapped, its evolution studied by minds that have transcended ordinary limitations of time and entropy. The image of its grand spiral form, long since unraveled, may still exist in archives that survive beyond stars, beyond black holes, beyond even the last remnants of ordinary matter. For now, this galaxy still turns, still shines, still plays its role in the vast cosmic dance. Its stars are not yet gone, its remnants not yet scattered to the cold depths of time. And as long as it exists, as long as light still escapes from its distant reaches, its presence in the universe remains undeniable. And even when its last light has faded, when its black holes have evaporated, when every particle has drifted into the background radiation of a silent cosmos, its existence will not have been a part of something far greater, a universe where time does not erase but instead transfer, energy does not disappear, new forms, where every celestial body, no matter how fleeting in the grand scale of eternity, contributes to the larger unfolding of reality. This galaxy's story may end in darkness, but it does not end in nothingness. It remains, always, a chapter in the infinite book of the cosmos, its essence forever imprinted upon the grand and unending tapestry of space and time. Even in the depths of an aging universe, where darkness slowly shone brightly, the essence of this galaxy endures. Its stars may fade, its structures may dissolve, and its energy may disperse into the vastness of space, but its influence, its mark upon the cosmic stage, remains. Every atom, every photon, every gravitational wave that ever emanated from this system is now part of something greater. The elements forged in its stellar cores have traveled far beyond its borders, carried by supernovae, stellar winds, and intergalactic currents to become part of new worlds, new structures, perhaps even new life. Though its own light may no longer shine, the echoes of its existence persist in ways beyond our current comprehension. If there are still observers, beings capable of witnessing the slow unraveling of the cosmos, they may look upon this galaxy not as a relic, but as a monument to the vast interplay of forces that have governed the universe since its birth. To them, it may serve as a record of everything that has come before, a cosmic archive written not in books but in the arrangement of dead stars, in the subtle distortions of spacetime left by its long past. Perhaps, in the farthest reaches of time, intelligence will still endure, outlasting even the stars themselves. If such minds exist, they may develop ways to resist the pull of entropy, to construct new energy sources in the universe. Perhaps they will find remnants of galaxies like this one, gathering their scattered pieces to forge something new in a universe that no longer creates but only erases. Even if no civilization survives, if no mind remains to remember, the fundamental laws of physics dictate that nothing will be lost. Energy changes form, matter disperses, structures dissolve, but the sum total of all that has ever existed continues to shape what will come next. This galaxy, even in its final silence, is part of that greater unfolding, its atoms scattered among the stars, its gravity still shaping the motion of celestial bodies long after its own light has faded. The universe does not forget, not in the way living beings do. The fabric of spacetime itself carries the imprints of everything that has ever been, the traces of every interaction, every force, every transformation. This galaxy, now only a whisper in the void, is woven into that vast, eternal record. And so, its journey does not truly end. It is not merely a structure that rose and fell in the unending expanse of time, but a contributor to something far greater. Whether the universe cycles anew, whether unknown forces bring about a rebirth, or whether entropy carries ever quiet and endless expansion, this galaxy will always have been part of the cosmic story. Its legacy is written in the light that once traveled across the stars, in the gravitational ripples it sent across space, in the elements it forged that now drift unseen among the ruins of a fading cosmos. It is a memory inscribed upon the infants that will never vanish. And as long as there are minds, whether now, in the distant future, or in some unknown epoch of reality, to look out into the dark and wonder, then its story, like the universe itself, will never truly be over. Even in the silent vastness of a universe approaching its final, unknowable fate, the existence of this galaxy remains an indelible part of the cosmic record. Though its stars have long since faded, their energy spent, their structures dissolved into the cold drift of intergalactic dust, the very fact that they once shone, that they once gave form to a grand and spiraling structure in the void, ensures that their influence is never truly erased. For now, the universe still expands, still carries the remnants of galaxies like this one outward into the growing abyss. If cosmic acceleration continues unchecked, then the final state of all things may be one of endless separation, an era where the last remaining fragments of matter are so distant from one another that no new structures can form, where even the faintest echoes of past galaxies are stretched across a universe that has grown too vast, too cold, too empty for anything to emerge anew. But even in such a fate, even in a universe that moves toward silence, the memory of this galaxy remains inscribed in the very fabric of space-time. Every gravitational wave it ever generated, every burst of energy it once released, every particle it sent drifting through the cosmos is now a part of something larger, a universe that has, for all its vastness, been shaped by each of its stars, each of its forces, each of its countless interactions. Perhaps, beyond even the longest timescales we can fathom, something new will arise from what seems to be an ending. Some theories suggest that the very structure of space itself may one day fluctuate, giving rise to new cosmic conditions, new particles, even new universes. Could it be that the energy of long-faded galaxies will one day serve as the seeds of something yet to be born? Could the remnants of matter, scattered across the vast, darkening cosmos, become the building blocks of a new cycle, a new age of light and structure? And if intelligence endures, if there are minds capable of witnessing the slow transformation of the universe into something beyond what we now understand, then they, too, may play a role in ensuring that this galaxy's legacy is not forgotten. Whether through archives stored beyond the limits of time, or through vast cosmic engineering projects that seek to resist entropy itself, there may still be those who hold the knowledge of what came before, who remember the age of galaxies, of stars, of motion and energy. Even if all else fades, even if no one remains to remember, this galaxy's story will have mattered. It was part of the great unfolding of the cosmos, an intricate symphony of forces that brought structure from chaos, light from darkness, form from formlessness. It existed, and that alone is enough to secure its place in the eternal record of all that has ever been. For now, its journey continues, its last remnants still drifting, still bound by the gravitational echoes of what it once was. And as long as the universe exists in any form, whether expanding into infinity, collapsing into rebirth, or transforming into something we cannot yet comprehend, this galaxy, and every atom that once belonged to it, part of the great and endless story of the cosmos. Even in the deep future, when the last remnants of matter drift in a universe grown vast beyond measure, the essence of this galaxy remains woven into the silent fabric of existence. Though no longer a luminous source, though its structures have dissolved into the slow tide of entropy, it was, and therefore it is. Its light once traveled across cosmic distances, its gravity once shaped the orbits of countless worlds, and its forces once played their part in the grand symphony of the cosmos. The universe itself is a memory, written not in ink but in the motion of celestial bodies, in the invisible distortions of spacetime left by the passage of stars, in the delicate balance of energy and void. This galaxy, long past its era of brilliance, has left its mark in ways that cannot be undone. The atoms forged in its core, scattered by supernovae billions of years ago, may still drift through space, waiting for a new gravitational well to gather them, to shape them into something yet to be. Perhaps no such rebirth will come. If the universe continues its expansion without bound, if no new structures can form, then matter itself may thin into nothingness, stretched by the relentless pull of dark energy. In such a future, the very idea of a galaxy, of stars and planets, will belong to a past so distant that it can no longer be reconstructed. The distances between remnants will grow so great that no interaction will ever occur again, no light will ever reach another point, no motion will ever again alter the stillness. And yet, even then, the trace of what once was will not be truly lost. The information of this galaxy's existence, of the energy it once radiated, of the forces it once exerted, will remain encoded in the quantum state of reality itself. Some physicists theorize that no information is ever truly destroyed, that even when stars collapse, when matter disintegrates, when black holes evaporate, the fundamental data of their existence persists in some unknown, hidden form. If this is true, then this galaxy, though long gone, will never have been erased. Perhaps, beyond the horizon of time, something will arise to read the final traces of what has been. Perhaps an intelligence beyond our comprehension, existing in a far future state where entropy has slowed, where the last pockets of energy are gathered and used with impossible precision, will find a way to reconstruct the past from its echoes. Perhaps the light of long-dead galaxies will be retrieved, played back in ways we cannot yet conceive, allowing some distant observer to witness the spiral arms once again, to see the stars as they were, to trace the paths of planets that no longer exist. And even if no mind survives to witness it, even if intelligence fades along with the last star, the fact remains that it was. This galaxy existed, it played its role in the cosmic battle, part of something immense, something unknowable. That alone secures its place in the infinite continuum of reality. The universe is vast beyond understanding, and time stretches forward into the unknowable. Yet within that vastness, every star that has ever shone, every world that has ever formed, every force that has ever acted upon matter has contributed to the larger unfolding of all that is. This galaxy, though now a ghost among the stars, was part of that story. It remains part of that story. And as long as the cosmos endures, its place in that endless, evolving narrative will never be undone. Even in the farthest reaches of eternity, where time itself stretches into the unknowable, the echoes of this galaxy persist. Though its stars have long since faded, though its structure has unraveled into the slow drift of forgotten remnants, it remains inscribed in the very essence of the cosmos. No moment, no force, no celestial motion is ever truly erased. All that has ever been continues to exist in the grand unfolding of reality, woven into the invisible fabric that binds all things together. The final remnants of this galaxy, white dwarfs long turned to black dwarfs, neutron stars reduced to frozen cores of dense matter, and black holes evaporating into the void, will persist until the very last motions of the cosmos come to a halt. If the universe continues to expand indefinitely, these fragments will drift apart, growing more isolated until they are separated by such great distances that even the fundamental forces of nature will no longer bind them together. Each will become a solitary traveler in an ever-darkening sea, cosmos where no new stars will ever ignite, where no light will ever again break the silence. Even in such an ending, the memory of this galaxy is not truly lost. If the nature of information is such that it cannot be destroyed, then every event that has unfolded here, every supernova that once ignited, every world that once formed, every star that once shone, still exists in some unfathomable way. The universe itself, as it once was, may be recoverable, its past encoded in ways beyond our current. Perhaps there will come a time, billions upon billions of years from now, when something, or someone, reaches into the deep archives of space-time and resurrects of this galaxy, reconstructing its stars, its planets, its structure from the echoes it has left behind. But even if no such recovery is possible, even if all knowledge is lost to entropy, the fact remains that it was. This galaxy existed. It was part of something vast, something beautiful, something impossible to fully grasp. It was a beacon in the night, a spiral of fire and motion, a place where matter danced in luminous patterns for a brief moment in the infinite. That moment may have passed, but its impact remains, woven into the grand design of the universe, forever a part of the great and infinite tapestry of existence. And so, as long as the cosmos endures, even in the cold and silent twilight of time's final stretch, the presence of this galaxy will never truly vanish. It will remain, an echo in the void, a whisper across eternity, a mark upon the unbroken continuum of all that has ever been. And so, as the universe drifts ever forward into the unknown, this galaxy's journey, though long past its most luminous days, remains part of the grand, unfolding story of the cosmos. It was a place of brilliance, where stars were born, where worlds may have formed, where forces beyond comprehension wove together light and matter into a vast and intricate dance. Though time has carried it towards stillness, though its stars have long since burned their last, its presence is not forgotten, it is etched into the very fabric of existence. For even when the last light has faded, even when the final remnants of matter dissolve into the expanding void, what was will always have been. This galaxy, like all things, played its part in the shaping of the cosmos, and that role, whether small or immense, cannot be undone. It is a whisper across the infinite, a moment of structure in an endless sea of transformation, a brief flicker of ordered motion before the quiet embrace of eternity. And though no mind may remain to remember, though no eye may look upon its spiraling form and marvel at its beauty, its essence will always be woven into the cosmic whole. It is not lost, nor meaningless, it is simply one chapter in the unending book of the universe, a chapter that will forever exist within the vast and unknowable expanse of time. For the universe is not static, nor is it finite in what it holds. As long as existence itself endures, as long as there is space and time in which new things may arise, nothing is ever truly gone. This galaxy's light may have faded, its matter may have scattered, its structure may have dissolved into the cosmic night, but it was, and that is enough. It remains, in echoes, in memories written into the physics of spacetime, in the particles that once formed its stars, now drifting toward futures yet unknown. And as long as the universe itself persists, its story, like all stories written in the fabric of the cosmos, will never truly end. The term Eye of God is often associated with celestial phenomena, most notably the Helix Nebula, NGC 7293. This planetary nebula, located approximately 650 light-years from Earth in the constellation Aquarius, has captivated astronomers and the general public alike due to its striking resemblance to a human eye. However, beyond its visual appeal, the Helix Nebula serves as a crucial subject for scientific investigation, offering insights into the life cycle of stars and the dynamics of interstellar matter. This nebula represents the final stages of a sun-like star's evolution. When a star exhausts its nuclear fuel, it expands into a red giant before shedding its outer layers, forming a luminous cloud of ionized gas. The central remnant, a white dwarf, emits ultraviolet, causing the ejected material to glow. The result is a stunning display of concentric shells of gas, rich in hydrogen, oxygen, and the intricate structure of the nebula, shaped by stellar radiation pressure, reveals the complex interplay between a dying star and its surrounding environment. Observations of this so-called cosmic eye have been instrumental in advancing our understanding of stellar death. Infrared imaging from telescopes like the Spitzer Space Telescope has allowed astronomers to analyze the composition of the nebula, detecting molecules such as carbon dioxide and silicates, essential building blocks for planetary formation. Meanwhile, the Hubble Space Telescope's high-resolution images have provided a detailed view of its intricate filaments and knots of gas, remnants of the star's outer layers interacting with the interstellar medium. The celestial iris is also a valuable laboratory for studying the transition of matter from stars back into the cosmos. As the nebula disperses over thousands of years, the elements it contains will eventually contribute to the formation of new stars, planets, and potentially even life-bearing worlds. This cyclical nature of stellar material underscores the interconnectedness of cosmic evolution. Beyond the Helix Nebula, other nebulae resembling an astral pupil exist throughout the universe, each offering unique insights into astrophysical processes. The Cat's Eye Nebula, NGC 6543, in the constellation Draco, for example, displays a highly complex structure, with multiple shells and a turbulent interior shaped by a binary star system. These observations suggest that planetary nebulae, despite their name, are far more intricate than early astronomers had assumed. From a broader perspective, the study of these so-called universal oculus structures is vital for understanding the fate of our own Sun. In approximately 5 billion years, our star will undergo a similar transformation, shedding its outer layers and leaving behind a dense white dwarf. By analyzing nebulae like the Helix, astronomers can predict how this process will unfold, offering a glimpse into the distant future of our solar system. Furthermore, the galactic lens concept extends beyond optical astronomy. Radio and X-ray telescopes have detected emissions from planetary nebulae, revealing energetic interactions between stellar remnants and their environments. These multi-wavelength observations help scientists piece together the puzzle of stellar evolution, uncovering processes that shape the universe at both microscopic and cosmic scales. The fascination with the heavenly gaze is not limited to professional astronomers. Public interest in these formations has been fueled by their striking imagery, often featured in popular science publications and space agency releases. The Helix Nebula, in particular, has been dubbed the Eye of God in cultural and artistic interpretations, symbolizing the vastness and mystery of the cosmos. As technology advances, new observational methods will allow scientists to further probe the depths of these stellar eyes. Upcoming space missions, such as the James Webb Space Telescope, promise to uncover finer details of nebular structures, shedding light on the physics of dying stars and their role in the cosmic cycle. By continuing to explore these celestial formations, we not only deepen our understanding of astrophysics but also reinforce humanity's connection to the universe. The ethereal vision, as seen in nebulae resembling a celestial eye, represents more than just the aesthetic marvel of the universe, it is a gateway to profound astrophysical insights. As observational techniques evolve, astronomers continue to unravel the complexities hidden within these cosmic structures, shedding light on the processes governing stellar evolution, interstellar chemistry, and the intricate balance between destruction and creation in the universe. One of the most intriguing aspects of the spectral gaze is the role planetary nebulae play in the chemical enrichment of the cosmos. Stars function as nuclear forges, synthesizing elements through fusion reactions over millions or billions of years. However, the true dissemination of these elements occurs during the final stages of a star's life. The Helix Nebula, like other similar structures, is rich in heavy elements such as carbon, oxygen, and nitrogen, materials that will eventually be incorporated into new generations of stars and planetary systems. Without this process, the fundamental building blocks of life would not exist, reinforcing the notion that planetary nebulae serve as crucial links in the cosmic cycle of matter. Recent observations using spectroscopic analysis have provided deeper insight into the composition of the celestial observer. By analyzing the emitted light at different wavelengths, astronomers have identified complex molecules and dust grains within these nebulae. The presence of polycyclic aromatic hydrocarbons, PAHs, organic molecules that form in the cooling gas of planetary nebulae, suggests that such regions may contribute to the organic inventory of the interstellar medium. This discovery has significant implications for astrobiology, as it indicates that the ingredients for life may be widely distributed throughout the universe, seeded by dying stars. Beyond their chemical contributions, the cosmic sentinel structures offer a glimpse into the physics of stellar winds and radiation-driven dynamics. The shaping of planetary nebulae is influenced by multiple factors, including the stellar wind from the progenitor star, magnetic fields, and even potential interactions with unseen companion stars. High-resolution imagery has revealed asymmetric structures, suggesting that many of these nebulae are not formed in isolation but are instead sculpted by gravitational interactions and external forces. For example, observations of the galactic observer using radio telescopes have unveiled the presence of collimated outflows, narrow, high-velocity streams of gas extending from the central star. These outflows, sometimes appearing as jets or bipolar lobes, provide evidence that the central white dwarf may have undergone interactions with an unseen companion, influencing the final distribution of expelled material. Such findings challenge earlier models that depicted planetary nebulae as simple, spherical shells and instead reveal a far more dynamic and chaotic process. Furthermore, the astronomical eye plays a role in the broader galactic ecosystem. The material ejected from these nebulae does not simply dissipate into the void, instead, it enriches surrounding molecular clouds, regions where new stars are born. This continuous recycling of stellar material ensures that each generation of stars contains heavier elements than the previous one, gradually shaping the chemical composition of galaxies over cosmic timescales. The study of these structures is poised for a major leap forward with the deployment of next-generation telescopes. The James Webb Space Telescope, JWST, with its unprecedented infrared capabilities, is expected to provide an even clearer view of the spectral lens, allowing astronomers to peer deeper into the dust-rich regions of planetary nebulae. By analyzing the thermal emissions from dust grains, scientists will gain insight into the temperature distribution and physical properties of nebular material, further refining our understanding of the late stages of stellar evolution. Beyond space telescopes, advances in computational astrophysics have allowed researchers to simulate the formation and evolution of the celestial portal. These simulations, incorporating fluid dynamics, radiation transport, and magnetic fields, are providing new models for how planetary nebulae develop over time. Some of the latest findings suggest that many of the intricate patterns observed in nebulae, such as filaments, arcs, and knots, are the result of instabilities in the stellar wind rather than external influences alone. Understanding these processes is essential not only for nebular studies but also for refining models of star formation and galaxy evolution. The enduring fascination with the universal aperture extends beyond professional astronomy. Throughout history, various cultures have interpreted celestial formations as divine symbols, and the appearance of an eye-like structure in space has only strengthened such associations. The Helix Nebula, in particular, has been widely featured in discussions about cosmic symbolism, often viewed as a metaphor for the universe observing itself. While such interpretations lie outside the realm of scientific inquiry, they highlight the profound psychological impact that astronomical imagery can have on human thought. As we continue to refine our observational tools and theoretical models, the Heavenly Sentinel remains a focal point of discovery. With each new dataset, astronomers are piecing together the puzzle of stellar death and rebirth, revealing the intricate interplay between individual stars and the vast cosmic web they help to shape. The more we study these celestial phenomena, the clearer it becomes that the universe is not a static entity but a living, evolving system, one where even the remnants of dying stars contribute to the emergence of new worlds. Thus, the ethereal observer is not just a spectacle to behold but a scientific treasure trove, holding secrets that continue to push the boundaries of human knowledge. Whether through advanced spectroscopy, deep space imaging, or theoretical simulations, each new discovery brings us closer to understanding the mechanisms that govern the cosmos and our own place within it. The cosmic observer, embodied in nebulae such as the Helix, remains an essential key to understanding the intricate dance of stellar birth, life, and demise. Each observation refines our grasp of the physical mechanisms that shape these celestial formations, providing new insights into the fate of stars, the dispersion of elements, and the ever-changing nature of the universe itself. One of the most compelling aspects of the astronomical aperture is its role in tracing the thermal and kinetic properties of gas expelled from dying stars. Observations across multiple wavelengths, from visible light to X-rays, have revealed that the temperatures within these nebulae can vary dramatically. The outer regions, composed of cooler gas, glow primarily in infrared and optical wavelengths, while the inner core, heated by the residual stellar remnant, emits in the ultraviolet and X-ray spectrum. This complex temperature gradient is a product of radiation interactions, with high-energy photons ionizing the surrounding material and gradually dissipating into space. Through high-resolution spectroscopy, researchers have uncovered that the stellar eye exhibits distinct velocity patterns, suggesting that the ejection of material is not uniform but rather occurs in pulses or waves. These periodic outflows likely result from fluctuations in the dying star's energy output, causing it to expel shells of gas at different rates over thousands of years. By studying these expansion rates, astronomers can estimate the age of planetary nebulae, offering a timeline for their formation and eventual dissipation. The Galactic Watcher is also central to the study of interstellar dust formation. As stars shed their outer layers, they release not only ionized gases but also microscopic solid particles, including silicates, carbonaceous grains, and even crystalline structures. These dust grains, once released into space, can act as seeds for future planetary systems. Studies of nebulae resembling the celestial portal have shown that these dust particles can survive for extended periods, eventually merging with molecular clouds where new stars and planets emerge. Understanding how these dust grains form, evolve, and disperse is crucial for unraveling the origins of complex planetary environments. Recent investigations using radio telescopes have revealed intriguing details about the magnetic fields within the universal lens. Magnetic interactions play a critical role in shaping the flow of ejected material, influencing the symmetry, or asymmetry, of planetary nebulae. Some of the most striking examples of these effects can be seen in nebulae with pronounced bipolar lobes, where charged particles are channeled along magnetic field lines, creating hourglass-shaped structures rather than simple spherical shells. The presence of such magnetic effects suggests that dying stars may possess previously undetected magnetic activity, adding another layer of complexity to our understanding of stellar evolution. The ethereal gatekeeper is not merely a relic of stellar death but a dynamic entity, continuously evolving as it expands into interstellar space. Observations indicate that as planetary nebulae disperse, they interact with their surroundings, sometimes triggering new star formation in nearby regions. Shock waves from these nebulae compress interstellar gas, creating dense pockets where gravity can take hold, potentially leading to the birth of new stars. This process, known as triggered star formation, highlights the interconnected nature of cosmic structures, where even the end of a star's life contributes to the genesis of another. Looking toward the future, next-generation astronomical instruments will further refine our understanding of the spectral sentinel. Ground-based observatories equipped with adaptive optics are already providing sharper views of nebular details, revealing previously unseen structures within these gaseous remnants. Space-based observatories, such as the James Webb Space Telescope, will allow astronomers to penetrate deeper into the obscured regions of planetary nebulae, uncovering the chemical and physical conditions within their dust clouds. Moreover, the study of the heavenly observer extends beyond individual nebulae to broader cosmic patterns. Comparing planetary nebulae across different galaxies has provided valuable insights into the chemical evolution of the universe. By analyzing the elemental abundances in distant nebulae, astronomers can trace how galaxies enrich themselves over time, revealing the gradual buildup of heavy elements essential for planet formation and, ultimately, life. The ongoing exploration of the celestial sentinel reinforces a profound truth: the universe is an ever-changing, interconnected system where every phase of stellar life contributes to the greater cosmic cycle. The dust and gas expelled by dying stars do not vanish into oblivion but instead become part of new cosmic structures, whether future planets, star-forming regions, or the diffuse interstellar medium that permeates galaxies. The continued study of these enigmatic formations is not just a quest for knowledge but also a reflection of humanity's deep-rooted curiosity about the cosmos. As we gaze upon these celestial eyes scattered throughout the universe, we are reminded that our own existence is intricately linked to the life cycles of the stars, that the atoms in our bodies were once forged in the hearts of ancient suns. Thus, the ethereal gaze remains both a scientific marvel and a cosmic symbol, a reminder that the universe itself is watching, evolving, and shaping the future in ways we are only beginning to comprehend. The celestial sentinel, as seen in the intricate formations of planetary nebulae, continues to serve as a window into the cosmic processes that govern the transformation of stars. Each observation adds new layers to our understanding of how these luminous remnants disperse their material, enriching the interstellar medium and influencing the next generation of celestial bodies. One of the most striking revelations about the cosmic watcher is the role of binary star systems in shaping nebular structures. While early models of planetary nebulae assumed a simple, spherical expansion of gas, modern high-resolution imagery has demonstrated that many of these formations exhibit asymmetric and highly complex shapes. Bipolar outflows, spiral patterns, and intricate filaments suggest the presence of secondary stellar companions that may interact gravitationally with the evolving nebula. These interactions lead to mass transfer, angular momentum redistribution, and the formation of dense equatorial rings or lobes of gas. Recent research into the galactic eye using data from the Atacama Large Millimeter/Submillimeter Array, ALMA, has provided unprecedented detail on the molecular composition of these nebulae. Scientists have detected not only simple molecules like carbon monoxide but also more complex organic compounds that suggest that nebular environments serve as chemical laboratories. These findings are crucial for understanding the origins of organic molecules in space, as planetary nebulae may act as dispersal points for the fundamental ingredients of life. Beyond their chemical complexity, the universal gaze nebulae also function as beacons of cosmic timekeeping. By measuring the expansion rates of different nebular shells, astronomers can determine how long a planetary nebula has been forming and predict how it will eventually fade into the interstellar medium. This timeline provides a framework for estimating the duration of different phases in stellar evolution, contributing to a broader understanding of how stars transition from red giants to white dwarfs. Additionally, X-ray observations of the spectral portal have revealed high-energy interactions occurring at the cores of some planetary nebulae. The remnant white dwarfs at the center of these formations often emit strong ultraviolet and X-ray radiation, which interacts with the surrounding gas to produce shock waves and ionized regions. These high-energy processes can influence the distribution of elements within the nebula, accelerating their dispersal and further enriching the surrounding galactic environment. The ethereal sentinel is not a static entity but rather a constantly evolving formation that continues to change even after the initial ejection of stellar material. Over time, the gas and dust within the nebula expand outward, gradually thinning as they mix with the surrounding interstellar medium. Eventually, after tens of thousands of years, the nebula will disperse completely, leaving behind only the white dwarf, a compact stellar remnant composed primarily of carbon and oxygen. However, the impact of the heavenly iris does not end with the fading of the nebula itself. The elements and molecules released by dying stars contribute directly to the formation of new stellar systems. Regions rich in planetary nebulae, such as the Orion arm of the Milky Way, contain some of the highest concentrations of interstellar dust and gas, making them prime sites for star formation. In this way, planetary nebulae act as catalysts for the next generation of cosmic evolution, ensuring that the cycle of stellar birth and death continues indefinitely. Future missions, such as the planned Extremely Large Telescope (ELT), and the next generation of space observatories, will provide even deeper insights into the structure of the astronomical eye. By using advanced spectrographs and adaptive optics, astronomers will be able to resolve individual knots of gas, trace their movements over time, and further refine models of how nebulae evolve under different conditions. The continued fascination with the stellar observer stems from both its scientific significance and its aesthetic grandeur. As one of the most visually striking phenomena in space, the Helix Nebula and its counterparts serve as reminders of the vast and intricate processes that shape the universe. They are not merely remnants of dying stars but active participants in the cosmic narrative, bridging the past and future of stellar evolution. In the grand scheme of the universe, the ethereal gateway stands as a testament to the interconnectedness of all cosmic phenomena. From the nuclear reactions within stars to the dispersal of elements across galaxies, planetary nebulae encapsulate the story of how matter cycles through the cosmos, influencing everything from the formation of planets to the potential emergence of life. As our observational capabilities expand and our theoretical models improve, the celestial guardian will continue to be a focal point of astronomical discovery. With each new revelation, we move one step closer to understanding not just the life cycle of stars, but the fundamental principles that govern the very fabric of the universe itself. The astral sentinel, embodied in planetary nebulae, represents a crucial phase in the grand cycle of stellar evolution. As researchers delve deeper into these enigmatic formations, they uncover new layers of complexity, revealing that the end of a star's life is not merely an endpoint but a transformative process that fuels the universe's ongoing dynamism. One of the most intriguing aspects of the Cosmic Guardian is its connection to white dwarf formation. The central star of a planetary nebula, having exhausted its nuclear fuel, contracts into a dense, hot core that will eventually stabilize as a white dwarf. These remnants, though small in size, typically no larger than Earth, contain the majority of the original star's mass, making them incredibly dense. Over billions of years, they will cool and fade, but their existence provides a glimpse into the fate of our own Sun. Studying these objects allows astronomers to predict how similar stars, including our own, will evolve in the distant future. Furthermore, the galactic sentinel plays a crucial role in regulating the composition of the interstellar medium. The gas and dust expelled by dying stars contain elements such as carbon, oxygen, and nitrogen, key ingredients for planetary formation. Without planetary nebulae dispersing these enriched materials, future generations of stars and planets would lack the necessary heavy elements to form rocky worlds, atmospheres, and potentially life. In essence, every terrestrial planet, including Earth, owes its existence to the contributions of ancient nebulae that came before. Recent advancements in radio and millimeter wave astronomy have provided new insights into the molecular processes occurring within the celestial guardian. Observations using the ALMA telescope have revealed the presence of molecular outflows that extend far beyond the visible boundaries of these nebulae. These outflows, composed of complex hydrocarbons and dust grains, suggest that planetary nebulae are not merely dispersing material into space but actively contributing to the chemical evolution of their host galaxies. Another critical discovery regarding the spectral watcher is the presence of highly structured ionization fronts within many nebulae. These ionization fronts occur when the intense radiation from the central white dwarf collides with the surrounding gas, creating sharp boundaries between ionized and neutral regions. These structures can appear as intricate filaments, knots, or even comet-like tails pointing away from the central star. The discovery of these fine details challenges previous models that assumed a more uniform expansion of planetary nebulae, indicating that localized instabilities and turbulence play a significant role in shaping these formations. In some cases, the heavenly vision has been found to exhibit signs of past violent interactions, possibly with unseen stellar companions. Certain planetary nebulae, such as the Necklace Nebula, display ring-like structures that suggest they were shaped by binary star interactions. When a dying star has a close companion, it can lead to complex mass exchange processes that produce symmetrical or spiral formations within the nebular shell. The presence of these structures suggests that planetary nebulae may serve as tracers for binary evolution, helping astronomers study the influence of stellar companions in shaping the final stages of stellar life. Looking ahead, the next generation of space telescopes promises to unlock even deeper secrets of the universal sentinel. The Nancy Grace Roman Space Telescope, set to launch in the coming decade, will provide wide-field surveys of nebular environments, allowing scientists to catalog planetary nebulae across vast regions of the Milky Way. Meanwhile, advancements in gravitational wave astronomy may one day allow us to detect the subtle imprints left by binary interactions within planetary nebulae, offering a new window into their hidden dynamics. Beyond their scientific value, the ethereal guardian formations continue to inspire philosophical and artistic interpretations. Their resemblance to eyes, portals, and celestial symbols has captivated the human imagination for centuries. Whether seen as the eye of God, a cosmic watcher, or a gateway to the unknown, these nebulae serve as reminders of the universe's vast and intricate beauty. They illustrate the cyclical nature of existence, where even the death of a star contributes to the formation of new worlds. Ultimately, the study of the astronomical sentinel reinforces one of the fundamental truths of astrophysics: the universe is in a constant state of transformation. Stars are not isolated entities but part of a vast cosmic network, where their births, lives, and deaths influence the evolution of galaxies. Every planetary nebula we observe today is a glimpse into this ongoing process, a snapshot of stellar material returning to the cosmos, ready to begin anew. As humanity continues to push the boundaries of space exploration and cosmic understanding, the celestial sentinel stands as both a scientific treasure and a poetic reminder of our place in the universe. Each discovery brings us closer to answering the fundamental questions of our existence: where did we come from? What will become of our sun? And how do the echoes of dying stars shape the fabric of space itself? With every new observation, the spectral guardian continues to reveal its secrets, guiding us deeper into the mysteries of the cosmos. The ethereal watcher, embodied in the grandeur of planetary nebulae, serves as a celestial archive of stellar evolution, a testament to the transformation of the universe across cosmic time. As these formations drift through the vastness of space, they offer not only a glimpse into the past but also a predictive model for the fate of future stars, including our own sun. One of the most fascinating aspects of the cosmic eye is its role in the feedback mechanisms that shape galactic structure. While often considered mere remnants of stellar death, planetary nebulae actively contribute to the ongoing evolution of their host galaxies. The gas and dust they expel enrich the interstellar medium, seeding future generations of stars with heavy elements. This process, known as chemical enrichment, is crucial for the formation of rocky planets, complex organic molecules, and even the conditions necessary for life. The study of the astronomical guardian has revealed that the dynamics of these nebulae are far more intricate than previously thought. Early models depicted planetary nebulae as simple, spherical shells of gas expanding uniformly into space. However, modern high-resolution imaging has uncovered a surprising diversity of shapes and structures, ranging from symmetrical ellipses to highly complex, asymmetric formations. Some nebulae display elongated lobes, others feature intricate filaments or even helical spirals, suggesting that multiple factors influence their morphology. One of the key drivers of these variations in the spectral sentinel is the presence of binary star systems. When a dying star has a close companion, gravitational interactions can significantly alter the shape of the resulting nebula. In some cases, the secondary star can siphon material from the primary, creating dense equatorial rings or spirals of gas that persist long after the initial ejection event. Observations of nebulae such as the Southern Crab Nebula and the Red Rectangle Nebula have provided compelling evidence that many planetary nebulae owe their distinctive appearances to binary interactions. Beyond their structural complexity, the galactic observer also plays a key role in astrophysical chemistry. Infrared spectroscopy has revealed the presence of complex organic molecules within planetary nebulae, including polycyclic aromatic hydrocarbons, PAHs, and fullerenes, carbon-based molecules shaped like spheres or tubes. These molecules, often associated with the building blocks of life, suggest that planetary nebulae serve as cosmic laboratories where the raw materials for planetary and biological evolution are forged. Their presence in nebular remnants reinforces the idea that organic chemistry is widespread throughout the galaxy and may be a fundamental component of planetary formation. Additionally, the Celestial Gateway is an ideal laboratory for studying the physics of radiation-driven winds. The interaction between the central white dwarf's intense ultraviolet radiation and the surrounding gas creates ionization fronts that propagate outward, sculpting the nebula structure over time. These processes are responsible for the bright, glowing edges and intricate internal patterns observed in many planetary nebulae. By studying these interactions, astronomers gain valuable insight into how stellar winds shape not only planetary nebulae but also the larger interstellar medium. Recent advancements in computational astrophysics have allowed researchers to simulate the formation and evolution of the universal sentinel with unprecedented accuracy. These models incorporate factors such as fluid dynamics, radiation pressure, and even magnetic fields to predict how planetary nebulae develop under different conditions. The results of these simulations have been strikingly consistent with real-world observations, confirming that planetary nebulae are shaped by a complex interplay of forces rather than simple expansion alone. The future of planetary nebula research is poised for dramatic advancements with the next generation of space telescopes. Instruments such as the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescope, ELT, will provide astronomers with deeper insights into the fine structure and chemical composition of these nebulae. With their enhanced sensitivity, these telescopes will allow scientists to probe nebulae at higher resolutions, tracing the flow of matter on scales previously unattainable. Moreover, the study of the heavenly sentinel has profound implications for understanding the fate of our own Sunday. In approximately 5 billion years, our star will enter the red giant phase before expelling its outer layers and forming its own planetary nebula. By analyzing existing nebulae, astronomers can predict what will happen to our solar system during this transformation. While Earth itself may not survive the Sun's expansion, the materials released in the process will contribute to the birth of new stars and planetary systems elsewhere in the galaxy, continuing the endless cycle of cosmic evolution. Beyond the realm of astrophysics, the ethereal observer has captured the imagination of artists, philosophers, and spiritual thinkers alike. Its striking resemblance to an eye has led many to interpret it as a cosmic symbol of awareness, a window through which the universe observes itself. Whether regarded as the eye of God, a portal to the unknown, or a reminder of our place in the vastness of space, these nebulae serve as powerful metaphors for the interconnectedness of all things. As our understanding of the astronomical eye deepens, so too does our appreciation for the intricate and dynamic processes that shape the cosmos. These nebulae are not merely remnants of stellar death, they are active agents in the grand story of creation, ensuring that the elements forged within stars continue their journey across the universe. With each new discovery, the spectral guardian reaffirms a fundamental truth: the cosmos is an ever-evolving, interconnected web where the past shapes the future. The atoms in our bodies were once part of dying stars, and one day, the material of our own sun will return to the galaxy, fueling the birth of new worlds. In this way, planetary nebulae remind us that nothing in the universe is ever truly lost, only transformed. The cosmic guardian, manifested in the grandeur of planetary nebulae, stands as a beacon of celestial transformation, bridging the life and death of stars in an unbroken cycle. These glowing remnants, scattered across galaxies, serve as more than mere artifacts of stellar demise. They are fundamental agents of change, shaping the universe in ways that extend far beyond their ephemeral lifespans. One of the most striking revelations about the ethereal lens is its role in the broader stellar ecosystem. The gas and dust expelled by these nebulae do not merely disperse into the void but actively participate in the cosmic recycling process. As they merge with the interstellar medium, these elements contribute to the birth of new stars, forming dense molecular clouds that serve as the cradles of stellar nurseries. This continuous exchange of material highlights the interconnectedness of all cosmic phenomena. No star, nebula, or galaxy exists in isolation, but rather as part of a vast, self-perpetuating system. Recent advances in spectroscopy have allowed scientists to probe deeper into the chemical composition of the galactic visionary, revealing an abundance of elements crucial for planetary and biological formation. Observations using the Hubble and James Webb Space Telescopes have confirmed that planetary nebulae are rich in oxygen, carbon, and nitrogen, elements that later become integral to the formation of solid planetary bodies and atmospheres. This process underscores a profound truth: without the dispersal of elements by dying stars, the conditions necessary for life as we know it could never arise. The structural complexity of the heavenly gatekeeper has also been a subject of intense research. While early depictions of planetary nebulae suggested simple, spherical expansions of gas, high-resolution imaging has shattered this notion, revealing intricate, asymmetrical patterns sculpted by unseen forces. Some nebulae exhibit jet-like outflows, others display strikingly symmetrical bipolar lobes, and still others form chaotic, filamentary networks. These diverse morphologies have led astronomers to investigate the underlying mechanisms responsible for such variations. One prevailing theory suggests that magnetic fields play a crucial role in shaping the universal watcher. While stars like the Sun are not typically associated with strong magnetic activity in their late stages, observations of planetary nebulae hint at unexpected magnetic influences. The interaction between stellar winds and magnetic fields could explain the presence of collimated jets and intricate loops within many nebular structures. If confirmed, this finding would redefine our understanding of the late-stage evolution of stars, suggesting that magnetic forces persist far longer than previously believed. Another significant factor influencing the morphology of the spectral portal is the presence of binary companions. Observations have shown that many planetary nebulae contain central stars locked in close orbits with unseen companions, dramatically affecting the way expelled material is distributed. In some cases, these interactions result in spiral formations, as seen in the stunning Necklace Nebula, where the gravitational influence of a secondary star has sculpted the ejected gas into a series of evenly spaced rings. Such discoveries suggest that planetary nebulae could serve as key indicators of binary evolution, offering new insights into the complex gravitational relationships between stars. Beyond their immediate impact on the interstellar medium, the astronomical sentinel also provides vital clues about the ultimate fate of stars like our Sun. By studying the energy output and cooling rates of the white dwarfs left behind at the center of these nebulae, astronomers can refine models predicting the long-term evolution of stellar remnants. White dwarfs, the ultra-dense cores of former giants, will spend billions of years slowly radiating away their heat until they become cold, dark remnants known as black dwarfs. Though no black dwarfs yet exist in the universe, since the timescale required for their formation exceeds the current age of the cosmos, planetary nebulae offer a glimpse into this distant, inevitable future. The celestial guardian is not merely a subject of scientific curiosity but also a source of inspiration and philosophical reflection. The striking resemblance of many planetary nebulae to an all-seeing eye has led to widespread cultural interpretations, reinforcing the idea that the universe itself is watching, evolving, and shaping new realities. In mythology and spiritual traditions, the eye is often a symbol of wisdom and perception, and its cosmic counterpart, found in nebulae like the helix, reminds us of the vast intelligence embedded in the workings of the universe. Looking ahead, the next frontier in the study of the ethereal observer lies in uncovering how these nebulae interact with larger cosmic structures. Do planetary nebulae influence the formation of spiral arms in galaxies? Could the shock waves from their expanding shells trigger supernovae in neighboring stars? As observational technology advances, astronomers are beginning to explore these larger-scale connections, piecing together the intricate web that binds stars, nebulae, and galaxies into a cohesive cosmic tapestry. With the deployment of more sophisticated instruments, such as the Extremely Large Telescope (ELT), and next-generation space observatories, our ability to observe and analyze the astronomical gatekeeper will reach unprecedented levels. These advances will enable researchers to detect fainter nebulae, track their evolution over time, and even identify planetary nebulae in distant galaxies, providing a broader perspective on their role in the universe's chemical and structural evolution. Ultimately, the study of the spectral watcher is more than an exploration of dying stars, it is a journey into the very fabric of cosmic creation. Every planetary nebula we observe today is a brief but brilliant chapter in a much larger story, a moment in time where a single star's legacy is written in light, gas, and dust. These nebulae are not mere relics of the past but active participants in shaping the future of galaxies, ensuring that the elements forged in stellar furnaces continue their journey across time and space. As humanity's knowledge of the galactic observer deepens, so too does our understanding of our own origins. The atoms in our bodies were once part of a dying star, just as future generations will be formed from the remnants of the Sun. In this way, planetary nebulae remind us that nothing in the universe is truly lost, only transformed, reborn into new stars, new worlds, and perhaps even new forms of life. Thus, the ethereal sentinel stands as both a cosmic masterpiece and a fundamental pillar of astrophysical inquiry. In its luminous beauty, we find the echoes of ancient stars, in its dynamic transformation, we glimpse the endless cycle of creation, and in its fleeting existence, we are reminded that the universe itself is a living, evolving entity, one in which every ending is, in truth, a new beginning. The celestial guardian, embodied in planetary nebulae, stands as an enduring testament to the impermanence and renewal of the cosmos. These breathtaking formations, fleeting in astronomical timescales yet integral to the cycle of stellar evolution, continue to shape the interstellar medium, leaving behind a legacy that extends far beyond the stars that birthed them. One of the most captivating aspects of the cosmic sentinel is its contribution to galactic evolution. As stars expel their outer layers, they inject vast amounts of enriched material into space, gradually altering the composition of their host galaxies. This ongoing chemical evolution ensures that each successive generation of stars forms from a medium increasingly abundant in heavier elements. Without the dispersal of carbon, oxygen, and nitrogen through planetary nebulae, the formation of rocky planets, complex chemistry, and potentially life itself would be far less common in the universe. Observations of the ethereal watcher have revealed its intricate interactions with surrounding interstellar clouds. As the expanding gas shell collides with nearby molecular clouds, it triggers shock waves that can compress and destabilize the gas, potentially initiating new episodes of star formation. In this way, planetary nebulae serve as catalysts for cosmic renewal, ensuring that the process of stellar birth continues long after their parent stars have faded. Moreover, the presence of planetary nebulae in ancient stellar populations provides insights into the life cycles of low to intermediate mass stars. By studying these nebulae in globular clusters and distant galaxies, astronomers can trace how the chemical composition of stellar populations has changed over billions of years. This research is crucial for understanding how galaxies like the Milky Way have evolved, from their early stages as simple gas clouds to their current complexity. At the heart of every planetary nebula lies a white dwarf, a remnant core that represents the final stage of stellar evolution for Sun-like stars. These dense, Earth-sized objects contain a once massive star, slowly radiating away their residual heat over billions of years. The study of these white dwarfs, facilitated by planetary nebulae, has provided invaluable insights into the behavior of degenerate matter and the physics of stellar cooling. Recent research has also suggested that some planetary nebulae may form in systems with multiple stellar components. In cases where a white dwarf exists in a binary system, mass transfer from a companion star can lead to a dramatic increase in its brightness, potentially triggering a nova, a sudden and powerful outburst caused by runaway nuclear reactions. These events add yet another layer of complexity to the role of planetary nebulae in shaping stellar evolution. The next generation of observational technology promises to revolutionize our understanding of the spectral observer. The Extremely Large Telescope, ELT, currently under construction, will offer unprecedented spatial resolution, allowing astronomers to resolve fine structures within nebulae with remarkable clarity. Additionally, new instruments such as the Nancy Grace Roman Space Telescope will provide wide-field surveys of planetary nebulae across diverse galactic environments, helping to refine models of their formation and evolution. Beyond optical astronomy, radio and X-ray telescopes will continue to probe the unseen aspects of planetary nebulae. X-ray observations, in particular, have revealed that some planetary nebulae contain hot, high-energy plasma, remnants of shock interactions between the expelled gas and the surrounding medium. These high-energy processes may play a significant role in dispersing nebular material over time, influencing the long-term fate of these structures. While planetary nebulae are primarily studied within the framework of astrophysics, they also occupy a special place in the human imagination. Their resemblance to eyes, celestial gateways, and ethereal forms has led many to interpret them as cosmic symbols of awareness and transformation. Across cultures, the eye has long been associated with knowledge, perception, and divine observation, and its counterpart in the stars, the Helix Nebula, often referred to as the Eye of God, has reinforced these associations. From a philosophical perspective, the heavenly sentinel serves as a reminder of the transient yet interconnected nature of all things. Stars are born, shine for millions or billions of years, and ultimately return their material to the cosmos, where it is reshaped into new stars, planets, and even living organisms. This cycle, echoed in the formation and dispersal of planetary nebulae, mirrors the broader principles of change, impermanence, and renewal that govern the universe. Ultimately, the study of planetary nebulae, the universal guardian of stellar evolution, offers profound insights not only into astrophysics but also into the broader mechanics of cosmic transformation. These nebulae are not merely the remnants of dying stars, they are active participants in the vast network of processes that shape the universe. From enriching the interstellar medium to triggering new waves of star formation, their impact is felt far beyond their luminous shells. As humanity's observational capabilities expand, so too does our understanding of the intricate dance between stellar life and death. The celestial guardian stands as a testament to the grandeur of cosmic evolution, a reminder that the universe is in constant motion, always shifting, reshaping, and preparing for what comes next. In the end, the story of the ethereal watcher is not just about stars, it is about us. The very atoms that make up our bodies were once forged in the hearts of ancient stars, released into space through the glowing remnants of planetary nebulae, and recycled into new worlds. In this way, we are all connected to the great cosmic cycle, living proof of the universe's ongoing symphony of creation and transformation. Thus, the spectral observer remains not only a scientific marvel but also a symbol of the endless possibilities that lie within the stars. It is a reminder that in every ending, there is a new beginning, an eternal cycle where the past shapes the future, and the light of dying stars illuminates the path toward new horizons. The astral gatekeeper, embodied in the ethereal glow of planetary nebulae, stands as a dynamic marker of the transition between stellar life and the vast interstellar medium. As these nebulae expand and disperse, they contribute not only to the ongoing chemical evolution of galaxies but also to the very fabric of cosmic transformation. Each one represents a singular moment in the grand cycle of star formation and death, a fleeting yet powerful display of nature's intricate processes. One of the most astonishing aspects of the celestial watcher is the diversity of its structures. No two planetary nebulae are exactly alike, despite originating from stars with similar masses. While some form near-perfect rings, others exhibit chaotic filaments, bipolar lobes, or even spiral arms stretching outward from the central star. This variety has led astronomers to investigate the external forces responsible for shaping these enigmatic formations. Among the leading explanations are magnetic fields, stellar winds, and the gravitational influence of unseen companion stars, each playing a role in determining a nebula's final appearance. As the expanding gas of the spectral guardian moves outward, its interactions with surrounding interstellar material create a series of shock fronts. These high-energy collisions result in the heating of the nebular gas, producing emission lines that reveal detailed information about its composition and motion. Spectroscopic studies using high-resolution telescopes have shown that different elements within a planetary nebula expand at different speeds, leading to layered structures where ionized hydrogen, oxygen, and nitrogen each form distinct glowing shells. The velocity of this expansion provides a crucial tool for determining the age of planetary nebulae. By measuring the outward motion of gas and extrapolating backward, astronomers can estimate when the ejection process began. Most planetary nebulae persist for only a few tens of thousands of years before they fade into the interstellar medium, making them relatively short-lived in astronomical terms. However, during this brief period, they serve as cosmic beacons, illuminating the processes that govern the final stages of stellar evolution. The galactic observer is more than a passive remnant of a dying star, it actively influences the environment around it. When the ejected gas collides with existing interstellar material, it can trigger star formation in nearby regions. This phenomenon, known as shock-induced star formation, occurs when compression waves create dense pockets of gas, providing the necessary conditions for gravitational collapse. In this way, the death of one star may directly lead to the birth of another, reinforcing the cyclical nature of cosmic evolution. Additionally, planetary nebulae provide an essential testing ground for understanding the life cycles of elements. The heavy elements expelled by these nebulae, carbon, oxygen, and nitrogen, become incorporated into future planetary systems, contributing to the formation of atmospheres and organic chemistry. Without the repeated enrichment provided by planetary nebulae, galaxies would remain chemically primitive, lacking the diversity of elements required for the complex chemistry seen in planets like Earth. One of the most compelling discoveries in recent planetary nebula research is the prevalence of binary systems among their progenitors. While single stars can produce relatively simple nebular shapes, binary companions introduce gravitational complexities that create strikingly intricate formations. In some cases, the companion star may even merge with the primary star, producing an especially dramatic ejection event. Observations of nebulae such as the Ant Nebula and the Hourglass Nebula have revealed spiral structures and bipolar outflows that suggest the presence of close-orbiting secondary stars. These formations provide valuable insight into the physics of binary evolution, offering clues about how stars exchange mass and energy in their final stages. Moreover, such interactions may play a role in the formation of more exotic astrophysical objects, including Type Ia supernovae, which occur when a white dwarf accumulates enough material from a companion to trigger a runaway nuclear reaction. As astronomical instruments become increasingly sophisticated, the study of planetary nebulae is entering a new era. The James Webb Space Telescope, JWST, has already begun to unveil previously unseen details within these structures, offering unprecedented insights into their dust composition, gas dynamics, and internal energy sources. Future missions, such as the proposed LUVOIR, Large Ultraviolet Optical Infrared Surveyor, promise to extend these observations even further, allowing astronomers to detect planetary nebulae in distant galaxies and study their role in galactic evolution. One of the key areas of ongoing research involves determining how planetary nebulae evolve over time. By observing multiple nebulae at different stages of expansion, astronomers can construct models that predict how they change, from the initial ejection of gas to their eventual dispersal into the interstellar medium. These models are crucial for understanding not only the fate of individual stars but also the broader mechanisms that drive galaxy-wide chemical enrichment. Beyond their scientific significance, planetary nebulae have long captured the human imagination. Their resemblance to eyes, portals, or celestial symbols has led to a variety of interpretations, from religious and mythological connections to philosophical reflections on the nature of existence. The so-called Eye of God, as the Helix Nebula is often called, serves as a reminder of humanity's enduring fascination with the cosmos, a visual representation of the universe's watchful gaze, as if observing its own creation and transformation. Many cultures throughout history have associated the eye with knowledge, perception, and enlightenment, and its celestial counterpart in planetary nebulae reinforces this symbolic meaning. The study of these nebulae not only advances our scientific understanding but also connects us to a deeper appreciation of the universe's complexity and interconnectedness. The celestial sentinel embodies one of the most profound truths in astrophysics, that creation and destruction are not opposing forces, but two sides of the same cosmic process. The death of a star is not an end but a transformation, a release of material that will go on to form new worlds, new stars, and perhaps even new forms of life. As our knowledge of planetary nebulae grows, so too does our awareness of our own place in this vast, interconnected system. The atoms that make up our bodies were once forged in the fiery cores of ancient stars, released into space through planetary nebulae, and recycled into the Earth and everything on it. In this way, we are direct descendants of the stars, a testament to the ongoing cycle of cosmic rebirth. With each new discovery, the spectral guardian continues to unveil its secrets, guiding us toward a greater understanding of the universe. As technology advances, we will peer deeper into these celestial formations, uncovering new layers of complexity and refining our models of stellar evolution. Yet, no matter how much we learn, planetary nebulae will always remain a source of wonder and inspiration, a reminder that the universe is alive with motion, change, and infinite possibilities. Thus, the ethereal gatekeeper is more than just a fleeting stellar remnant, it is a symbol of continuity, a beacon of cosmic renewal, and a bridge between the past and the future. In its glowing filaments and radiant shells, we see the echoes of dying stars and the promise of worlds yet to be born, an eternal testament to the ceaseless transformation of the cosmos. The celestial sentinel, a luminous remnant of a once mighty star, remains a crucial player in the grand narrative of the universe's continuous transformation. Each planetary nebula represents both an ending and a beginning, an ephemeral moment when a dying star sheds its outer layers, only for that material to merge back into the vast interstellar medium, eventually seeding the birth of new stars and planetary systems. As these nebulae drift across the cosmos, they shape the evolution of galaxies, enrich the fabric of space with essential elements, and provide key insights into the physics of stellar life cycles. One of the most remarkable properties of the cosmic guardian is the way it interacts with radiation. The central white dwarf, a remnant of the original star's core, continues to emit intense ultraviolet light, ionizing the surrounding gas and causing it to glow. This process is responsible for the striking colors observed in planetary nebulae, with different elements emitting light at characteristic wavelengths. Oxygen typically glows green or blue, while nitrogen and hydrogen produce red and pink hues, forming the beautiful, otherworldly patterns seen in nebular images. The ionization process does more than illuminate the nebula, it actively shapes its evolution. As the gas absorbs radiation and heats up, it expands outward, creating pressure waves that interact with surrounding material. Over time, the nebula's structure changes, with dense knots of gas forming where matter clumps together, while other regions thin out as the gas disperses. These dynamic processes make each planetary nebula a living, evolving structure rather than a static remnant. New studies using infrared and radio telescopes have revealed the presence of dust grains within these nebulae, suggesting that planetary nebulae contribute significantly to the galactic dust cycle. This dust, composed of silicates, carbon compounds, and complex organic molecules, eventually integrates into star-forming regions, influencing the development of protoplanetary disks around young stars. This connection further underscores the role of planetary nebulae in the grand cycle of cosmic renewal. As the glowing clouds of a planetary nebula expand, they eventually fade into the background of the galaxy, leaving behind only a compact white dwarf. These stellar remnants, the end state of sun-like stars, are among the densest objects in the universe. Composed primarily of carbon and oxygen, they no longer generate energy through fusion but continue to radiate heat for billions of years. Over time, they cool and fade, becoming black dwarfs, though no black dwarf yet exists, as the universe is not old enough for any white dwarf to have fully cooled. Recent research into the cooling rates of white dwarfs associated with planetary nebulae has provided a new tool for measuring cosmic time. By studying the thermal evolution of these objects, astronomers can estimate the ages of stellar populations in different regions of the galaxy, refining our understanding of galactic formation and evolution. One of the most intriguing aspects of planetary nebulae is their potential connection to Type Ia supernovae. In binary systems where a white dwarf accumulates material from a companion star, it may eventually reach a critical mass, triggering a runaway nuclear reaction and resulting in a powerful explosion. These supernovae play a vital role in dispersing heavy elements across the cosmos and serve as standard candles for measuring astronomical distances. While not all white dwarfs in planetary nebulae reach this stage, their existence highlights the diverse evolutionary paths of stellar remnants and the profound role they play in shaping the chemical composition of the universe. Advancements in observational astronomy have revealed unexpected complexities in these nebulae, challenging earlier models of their formation. High-resolution imaging has uncovered intricate structures such as concentric shells, spirals, and dense knots of gas shaped by radiation pressure and stellar winds. Some nebulae, like the Cat's Eye and the Eskimo Nebula, feature layered envelopes, indicating multiple episodes of mass ejection separated by thousands of years. These findings suggest that the formation of a planetary nebula is not a singular event but a prolonged and dynamic process, where material is released in stages rather than expelled all at once. The diverse morphologies of planetary nebulae result from a combination of factors, including magnetic fields, binary star interactions, and variations in stellar wind intensity. These forces sculpt the nebulae into highly asymmetrical shapes, ranging from elliptical and bipolar structures to complex filaments and arcs. In some cases, interactions with interstellar clouds further distort their expansion, producing crescent-like formations. These interactions not only alter their appearance but also provide insights into the movement of stars within galaxies and the distribution of cosmic material. As astronomical technology advances, planetary nebulae are becoming more accessible to detailed study. The James Webb Space Telescope, JWST, has already begun revealing hidden molecular components within these nebulae, uncovering previously undetected compounds that may play a role in interstellar chemistry. At the same time, radio telescopes such as ALMA, Atacama Large Millimeter/Submillimeter Array, are mapping the distribution of cold gas and dust, offering a more complete understanding of their long-term evolution. These studies help astronomers piece together how planetary nebulae enrich the interstellar medium, seeding future generations of stars and planets. Future missions, including the Extremely Large Telescope, ELT, and the Nancy Grace Roman Space Telescope, will allow scientists to detect fainter nebulae in distant galaxies. By analyzing their composition and distribution, researchers will gain insights into how planetary nebulae contribute to the ongoing chemical evolution of different stellar populations across cosmic time. Additionally, advancements in computational modeling are enabling astronomers to simulate the formation and transformation of these nebulae with increasing accuracy. Incorporating elements such as fluid dynamics, radiation pressure, and magnetic interactions, these models bring us closer to understanding the full range of processes shaping these celestial structures. Beyond their scientific significance, planetary nebulae hold a deep symbolic and philosophical meaning. Their striking resemblance to eyes, portals, and celestial watchers has long captivated human imagination, inspiring artistic and spiritual interpretations. The Helix Nebula, often called the Eye of God, serves as a reminder of the vastness of the cosmos and humanity's enduring quest to understand its mysteries. These glowing remnants of once mighty stars invite contemplation, prompting us to reflect on the cycles of existence, the impermanence of all things, and the continuous transformation of matter and energy throughout the universe. At their core, planetary nebulae are more than just the remnants of dying stars. They are cosmic forges, dispersing elements that will one day coalesce into new stars, planets, and potentially even life itself. The oxygen in our atmosphere, the carbon in our bodies, and the nitrogen in our DNA were all forged in the fiery hearts of long-extinct stars, then cast into space through planetary nebulae before becoming part of new planetary systems. This grand cycle of stellar birth, death, and rebirth is not just an abstract astrophysical concept, it is the very process that made our own existence possible. Ultimately, planetary nebulae serve as bridges between stellar death and the creation of new celestial structures. Their ethereal beauty and scientific significance remind us that the universe is in a constant state of transformation. These nebulae are not merely fading echoes of dying stars but the seeds of future worlds. As they expand and disperse, they enrich the universe with the raw materials needed to form new stars, planetary atmospheres, and the chemical foundations of life. Through each new observation and discovery, we are not just studying the evolution of stars, we are witnessing the cosmic mechanisms that govern the universe itself. Planetary nebulae, fleeting in their lifespans yet essential in their contributions, remind us that nothing in the universe is truly lost. Every dying star contributes to the formation of new worlds, and every planetary nebula carries within it the legacy of past generations of celestial objects. The celestial guardian stands as both a scientific marvel and a profound cosmic symbol. It embodies the endless cycle of birth, destruction, and renewal that defines the universe. As we continue to explore these luminous remnants, we are not only uncovering the secrets of distant stars but also deepening our understanding of our own cosmic origins. In the vast and ever-changing cosmos, planetary nebulae remind us that the universe itself is a living, evolving entity, one where every ending is a new beginning, and every atom of our existence once belonged to a star that shone in the ancient night. Hyperspeed galaxies are among the most mysterious and extreme objects in the universe. Unlike most stellar systems that remain gravitationally bound to larger structures, these fast-moving formations travel at incredible velocities, often thousands of kilometers per second, raising profound questions about their origins and fate. One of the biggest unknowns is whether such galaxies ever stop. While space is nearly empty, there is still a thin haze of intergalactic gas, dust, and dark matter that could create a form of cosmic drag over billions of years. This resistance, although weak, might gradually slow down some of these high-velocity systems. Another possibility is that they experience tidal interactions with gravitational waves, subtly altering their motion over time. Some models suggest that heat death and energy dissipation across cosmic timescales might eventually leave them as cold, dark, and isolated masses drifting endlessly through the void. An alternative hypothesis suggests that these galaxies are not simply being flung into space but are actually being pulled towards something massive and unknown. Some cosmologists propose that beyond our observable universe, a hidden gravitational attractor could be exerting influence on entire clusters. If these high-speed galaxies appear to accelerate in the same direction, they could be heading toward a vast structure or even another universe. Within the Laniakea supercluster, galaxies appear to move toward an unexplained mass known as the Great Attractor. If similar anomalies exist on even larger cosmic scales, fast-traveling galaxies could be responding to these unseen forces. Conversely, instead of being drawn toward a mass concentration, they might be repelled by voids, massive underdense regions that create gravitational imbalances. Tracking their trajectories over millions of years could help astronomers identify these hidden structures. Another possibility is that some of these galaxies could be escaping the universe itself. If space is expanding at an accelerating rate, certain objects may reach the cosmic event horizon, a boundary beyond which they recede faster than the speed of light due to spacetime expansion. From our perspective, they would fade into infrared darkness, never to be seen again. If one of these high-velocity galaxies breaks free from the cosmic web, the large-scale structure of interconnected galaxies and dark matter filaments, it may enter a completely empty region of space where gravitational interactions are minimal. Some physicists speculate that if spacetime has hidden topologies, wormholes, or interdimensional pathways, such a galaxy could theoretically exit into another universe, making it unobservable forever. If astronomers detect a stellar system that appears to be vanishing without explanation, it could provide the first direct evidence of such an event. While most of these galaxies are thought to move away from major structures, some might eventually collide with others at extreme velocities. A high-speed impact between two galaxies traveling at thousands of kilometers per second would release unimaginable amounts of energy, possibly creating an entirely new class of high-energy astrophysical events. Such a hypercollision could trigger the most violent starbursts ever observed, compressing gas into dense clouds that rapidly form new stars. However, it could also lead to the destruction of galactic structures, tearing apart stellar systems and forming long tidal streams of stars and gas stretching across millions of light-years. If one of these fast-moving galaxies collides with a normal galaxy, it might even lead to the formation of an ultramassive black hole, disrupting the gravitational balance of its surroundings. Detecting such an event would provide valuable insights into the limits of cosmic energy transfer and the behavior of galaxies under extreme conditions. Another strange idea is that some of these galaxies might not be what they seem. Certain anomalies in their motion could indicate that they are faint relics from the early universe. If a galaxy formed soon after the Big Bang and was ejected at high speed, its light might only now be reaching us, making it appear as though it exists in a different cosmic epoch. Others proposed that some of these high-velocity galaxies could be composed mostly of dark matter, making them nearly invisible except for their gravitational effects. If such formations exist, they could be drifting through space largely undetected, interacting only through gravity. Even more speculative is the idea that some of these fast-traveling galaxies might be holographic projections or manifestations of unknown physics, possibly revealing hidden dimensions or an emergent cosmic order. Future deep space surveys could help determine whether they are entirely normal objects or something far stranger. If an intelligent civilization evolved inside one of these high-velocity galaxies, its experience of the universe would be radically different from our own. Due to relativistic time dilation, time for the inhabitants of such a galaxy would slow down compared to the rest of the cosmos. If their stellar system were moving at a significant fraction of the speed of light, billions of years could pass for the outside universe while only a few thousand years pass for them. The motion of their galaxy through intergalactic space would also expose them to extreme cosmic radiation, which could require either advanced shielding technologies or biological adaptations to survive. If such a civilization were aware of their home galaxy's extreme velocity, they might attempt to influence it either to slow it down or to direct it toward a particular region. If astronomers ever detect anomalous energy signatures or signals from a fast-moving galaxy, it could be evidence of an advanced civilization adapting to an extreme cosmic environment. Future telescopes such as the James Webb Space Telescope, the Vera Rubin Observatory, and new gravitational wave detectors will allow scientists to study ultra-fast galaxies in greater detail. Among the most anticipated discoveries is the detection of the first relativistic stellar system, one moving at over 50% of the speed of light, which would challenge our understanding of gravity and dark matter. Another breakthrough could be finding a high-velocity galaxy that unexpectedly changes trajectory, suggesting the influence of unknown forces or even artificial manipulation. If one of these cosmic travelers is observed to vanish completely, it might be observational evidence of cosmic gateways, wormholes, or higher dimensional structures. Additionally, detecting a galactic hypercollision would reveal how energy transfers at the largest scales. The study of these extreme objects remains one of the most exciting frontiers in astrophysics. Whether they result from gravitational interactions, unknown cosmic forces, or even signs of intelligent engineering, such fast-moving galaxies push the boundaries of what we consider possible. As observational capabilities improve, we may soon uncover their true nature, possibly redefining our understanding of space, time, and the fate of the universe. If these high-speed galaxies exist in significant numbers, they may not be isolated anomalies but rather part of a greater cosmic pattern that has yet to be fully understood. Their existence challenges current astrophysical models, pushing the limits of our knowledge about gravity, cosmic expansion, and galactic evolution. They could also be linked to the formation of large-scale structures, revealing an unknown mechanism governing their motion at extreme velocities. One intriguing possibility is that these galaxies are not randomly propelled but instead follow gravitational highways formed by dark matter filaments. Some cosmologists propose that dark matter is distributed in a way that creates massive intergalactic superhighways, allowing certain stellar systems to move faster than expected. If this is true, these cosmic wanderers could provide crucial evidence about the large-scale structure and distribution of dark matter in the universe. Another theory suggests that fast-moving galaxies might be influenced by cosmic voids, vast empty regions with little to no matter. Instead of being pulled toward massive objects, these stellar formations could be repelled by these underdense regions, accelerating outward. Some scientists speculate that dark energy, the mysterious force driving the universe's expansion, might have local variations that push galaxies away rather than simply expanding space uniformly. If such galaxies are disproportionately found near cosmic voids, this could suggest that dark energy is more complex than previously thought. There is also the possibility that unknown fundamental forces accelerate these galaxies. While standard physics describes gravity as the dominant force at cosmic scales, alternative theories propose additional interactions affecting galaxies and clusters. If ultrafast galaxies accelerate in ways that cannot be explained by known gravitational effects, this could indicate the presence of a new fundamental force shaping the universe. Some researchers speculate that these stellar systems might be relics from an earlier phase of cosmic evolution. If physical laws or interactions between matter and dark matter differed in the early universe, certain galaxies may have been propelled to extreme velocities billions of years ago. This could mean that rather than being anomalies, these objects are remnants of a primordial event, offering insight into physics that no longer operates today. Another question is whether some of these galaxies might be artificial. If an advanced civilization had technology capable of manipulating gravitational fields, it could potentially control the motion of an entire galaxy. This could be done to escape a dangerous region of space, navigate toward a desired location, or even use galactic movement as a form of interstellar travel. If astronomers detect high-speed galaxies exhibiting controlled acceleration rather than purely natural motion, it could be a sign of large-scale engineering at work. Future observations will be crucial in determining whether these galaxies fit within known physical models or require new physics to explain their behavior. By analyzing their motion, astronomers may identify patterns revealing whether they travel randomly or as part of a larger cosmic structure. If they follow dark matter filaments, this could confirm the existence of gravitational highways shaping the universe. If they are concentrated near cosmic voids, this might indicate a previously unknown interaction between galaxies and dark energy. One of the most important breakthroughs could come from tracking the long-term trajectories of these cosmic speedsters. If their motion changes unexpectedly, defying known gravitational dynamics, it could suggest the presence of undiscovered forces. Additionally, if some of these galaxies appear to accelerate rather than simply maintaining constant speeds, this might indicate an unknown influence on their movement. Another groundbreaking discovery would be finding galaxies that appear to vanish. If a stellar system moves at extreme velocities and later disappears from observations, it might have crossed a cosmic boundary, such as the event horizon created by space expansion. This could provide direct evidence of galaxies escaping the observable universe, an idea long theorized but never confirmed. As observational technology advances, allowing astronomers to detect fainter and more distant objects, the study of ultrafast galaxies will enter a new era. Next-generation observatories, including the Square Kilometre Array and upgraded gravitational wave detectors, may uncover unknown aspects of galactic motion and interactions. If these high-velocity objects turn out to be more common than expected, it would suggest that the universe is far more dynamic than current models predict. Ultimately, these extreme galaxies could hold the key to solving some of cosmology's deepest mysteries. Whether they result from dark matter interactions, repulsion from voids, remnants of an ancient event, or even artificial constructs, their existence challenges fundamental astrophysical assumptions. Their study could not only redefine our understanding of galaxy evolution but also reshape our view of the universe itself. If these galaxies are more than just isolated anomalies, their movement could indicate that the universe's large-scale structure is far more active than previously thought. Their acceleration might be governed by unknown interactions between dark matter, dark energy, and intergalactic gravitational fields. If their motion cannot be fully explained by known mechanisms such as gravitational slingshots or black hole interactions, it could suggest that vast regions of space experience forces yet to be discovered. One of the most compelling possibilities is that these objects are responding to unknown gravitational waves or distortions in spacetime. If large-scale ripples in spacetime exist, perhaps caused by ancient cosmic events like the collision of supermassive black holes or remnants of a previous universe, they might subtly influence galaxy trajectories across billions of light-years. Future gravitational wave detectors could determine whether these galaxies are reacting to spacetime distortions beyond our current detection capabilities. Another intriguing question is whether these galaxies are linked to variations in dark energy. While dark energy is generally considered uniform, if high-speed galaxies tend to move toward or away from specific regions, it could mean that this force is unevenly distributed. Some parts of space might exert stronger repulsive forces, pushing entire galaxies to extreme velocities. If true, this would require a major revision of cosmological models, suggesting a far more complex expansion of the universe. It is also possible that these stellar formations reveal a new type of matter or interaction. If some galaxies accelerate in ways inconsistent with standard gravitational models, they might be affected by unknown particles or forces. For instance, if dark matter is not entirely passive but exhibits certain repulsive or dynamic properties under specific conditions, it might explain the unusual acceleration patterns observed. Alternatively, an undiscovered force acting at cosmic scales could first reveal its effects through these galaxies. A more radical idea is that these high-speed objects interact with hidden dimensions. Some string theory models propose that gravity may leak into additional spatial dimensions, causing unexpected deviations in galactic motion. If such galaxies are disproportionately found in certain regions of space, they might be interacting with higher dimensional structures, providing the first observational hint of extra dimensions. Another fascinating concept is whether ultrafast galaxies function as natural time machines. Due to relativistic effects, objects moving at extreme velocities experience significant time dilation, where time slows relative to the rest of the universe. If a galaxy were moving near the speed of light, an external observer might witness it aging much more slowly than surrounding cosmic structures. If civilizations exist within such galaxies, they could experience time on a vastly different scale, effectively becoming time travelers relative to the broader universe. The detection of these galaxies also raises fundamental questions about their long-term fate. If they continue accelerating, do they reach a threshold beyond which they can no longer interact with the rest of the universe? If so, does this imply the existence of cosmic escape routes, where matter can permanently exit the observable cosmos? If one of these stellar systems were to cross such a boundary, it might appear to slow and fade from view, eventually becoming undetectable. Observing such a disappearance would be among the most extraordinary discoveries in modern cosmology. Another consideration is whether ultrafast galaxies are indicators of an impending phase transition in the universe. If more of these stellar systems are found accelerating to extreme velocities over time, it could suggest a fundamental cosmic shift, possibly signaling a transition into a new state of physics. Some theoretical models propose that dark energy may eventually increase in strength, leading to the so-called Big Rip scenario, where galaxies, stars, and even atoms are torn apart as space expands at an accelerating rate. If these fast-moving galaxies are early signs of this process, they may be the first objects to reveal that the nature of the cosmos is evolving in ways we do not yet fully understand. As more advanced telescopes and computational models emerge, astronomers will be able to analyze high-velocity galaxies with unprecedented precision. If patterns emerge in their motion, they could reveal an underlying structure governing their trajectories. Some of these objects might also display unexpected compositions or energy signatures, suggesting interactions with forces beyond current understanding. Whether propelled by dark matter streams, gravitational distortions, or something even more exotic, these galaxies remain among the most enigmatic mysteries of the cosmos. The study of such extreme celestial objects has the potential to reshape our understanding of fundamental cosmic forces. Whether they are remnants of a previous cosmic cycle, indicators of hidden physics, or evidence of an undiscovered aspect of dark energy, their presence challenges the assumption that the universe is predictable and stable. Instead, they suggest a far more dynamic cosmos, where extreme motion and unknown interactions may one day redefine everything we know about space, time, and reality itself. If increasing numbers of fast-moving galaxies continue to be discovered, it could indicate that our understanding of the universe remains fundamentally incomplete. Their existence challenges traditional models of galaxy motion, hinting at unexpected forces at play or unknown interactions with cosmic structures. Future studies could determine whether these galaxies are simply anomalies or part of a larger, hidden pattern in cosmic evolution. One of the most crucial areas of research will be the long-term tracking of these cosmic travelers. If they exhibit variations in velocity or unexpected trajectory shifts, it could imply interactions with variable gravitational forces or invisible structures. Such deviations from expected motion would provide direct evidence of uncharted cosmic phenomena, potentially revealing undiscovered cosmic forces or gravitational anomalies. Advanced simulations and AI-driven analysis will be essential in mapping their paths and predicting their future movements. Another question is whether these galaxies interact differently with cosmic expansion. The accelerated expansion of the universe is attributed to dark energy, but hyperfast galaxies could provide new insights into how high-velocity objects behave within an expanding spacetime. If their movement deviates from standard cosmological expectations, it might suggest that space itself has hidden dynamics influencing their trajectories. Observing them over long time frames may offer clues as to whether space contains unknown factors that affect galaxies at extreme speeds. The role of dark matter in the motion of these high-speed stellar systems is another key question. If they exhibit velocities inconsistent with visible gravitational sources, it could suggest that dark matter plays a more active role in shaping their movement. Some theories propose that dark matter might not be entirely passive but could instead interact dynamically under specific conditions, forming invisible gravitational currents that direct galaxies along particular paths. If ultrafast galaxies are following these hidden flows, it would provide compelling evidence for the structure and behavior of dark matter on cosmic scales. There is also the possibility that these galaxies are linked to exotic astrophysical processes. Some hypotheses suggest the existence of previously unknown gravitational slingshot mechanisms capable of imparting immense velocity to entire stellar systems. If new classes of astrophysical events, such as interactions with rogue supermassive black holes or large-scale gravitational waves, are discovered, they could help explain why some galaxies achieve such extreme speeds. Investigating the environments around these objects could reveal whether they originate from regions of high gravitational instability. Another avenue of research is whether high-velocity galaxies represent a previously unknown evolutionary pathway for galactic systems. If some galaxies are ejected from dense clusters or experience prolonged high-speed motion through intergalactic space, they may undergo unique evolutionary processes. A galaxy moving at extreme velocity might lose its gas more rapidly, reducing its ability to form new stars. Over time, it could evolve into a dark, inactive system, devoid of significant star formation. If astronomers identify quiescent galaxies that appear to have once been high-speed objects, it could indicate that these stellar systems aged differently due to their extreme motion. Another intriguing possibility is that rapidly moving galaxies could serve as natural laboratories for testing relativistic physics on a galactic scale. Since objects moving at near-light speeds experience time dilation and other relativistic effects, their internal physics may subtly differ from stationary galaxies. If ultrafast galaxies exhibit unusual energy distributions or unexpected cosmic ray activity, they could provide an unprecedented real-world test of Einstein's theories at galactic scales. The potential for these galaxies to reveal hidden cosmic structures is another key area of study. If they consistently move toward or away from specific regions of space, it could suggest the presence of unseen mass concentrations, variations in dark energy, or even exotic gravitational anomalies. Some researchers speculate that hyperfast galaxies may act as natural probes of the universe's invisible framework, uncovering structures that otherwise remain undetectable. Large-scale surveys mapping their trajectories could provide new insights into the hidden architecture of spacetime. The ultimate fate of these galaxies remains uncertain. If one is moving at extreme speeds, does it eventually slow down due to cosmic interactions, or does it continue accelerating indefinitely? If some appear to gain velocity over time, it might indicate interactions with large-scale cosmic flows or even hidden dimensions. Conversely, if they eventually decelerate, it could suggest that intergalactic drag, dark matter interactions, or unknown gravitational effects gradually reduce their energy over billions of years. If any of these galaxies were observed to vanish from astronomical surveys, the implications would be profound. Such a discovery might suggest that certain galaxies are crossing into regions of space fundamentally different from our own, potentially supporting theories of cosmic gateways, wormholes, or even the multiverse. If a fast-traveling galaxy were to disappear without a trace, it would be among the most extraordinary astronomical findings in history, requiring a radical reconsideration of cosmic boundaries. As technology advances, the study of ultra-fast galaxies is likely to become one of the most significant fields in astrophysics. The ability to track them over millions or even billions of years could help resolve some of the biggest questions about the structure and evolution of the cosmos. Whether they reveal new forces, uncover exotic physics, or simply challenge our understanding of gravity on the largest scales, these extreme galaxies could hold the key to the next great discoveries in astrophysics. If these high-speed objects are part of a larger, hidden structure within the universe, their continued study may unveil aspects of the cosmos that remain undetected. They could be following unseen gravitational currents, responding to forces beyond our current understanding, or even moving toward a final destination beyond the limits of observable space. Their behavior might be signaling the presence of undiscovered cosmic phenomena, making them one of the most promising astrophysical mysteries of our time. One of the biggest questions surrounding ultra-fast galaxies is whether their trajectories are entirely random or if they exhibit patterns that suggest an underlying order. If their motion aligns with large-scale structures, such as cosmic filaments or dark matter streams, it would provide strong evidence that these stellar systems interact with an invisible framework shaping the movement of matter across billions of light-years. Future deep space surveys will be crucial in determining whether these galaxies follow specific paths or are simply the result of chaotic gravitational interactions. The possibility that hypervelocity galaxies are connected to large-scale cosmic expansion raises additional questions. If they are accelerating beyond expected limits, it could indicate that space itself does not expand uniformly. Some cosmologists propose that different regions of the universe may expand at varying rates due to fluctuations in dark energy density. If these high-speed galaxies are concentrated in areas of anomalous expansion, it might suggest that the acceleration of the universe is more complex than previously thought. Another potential factor influencing these fast-moving stellar systems could be unknown astrophysical events. While many are believed to have been ejected due to interactions with supermassive black holes or gravitational slingshots within dense clusters, there may be other unidentified mechanisms at play. If some galaxies reach extreme speeds without any apparent interactions, it could indicate the existence of new cosmic forces, undiscovered astrophysical explosions, or interactions with exotic forms of matter. A more radical hypothesis suggests that these galaxies might be revealing new physical laws that only become apparent on extremely large scales. In standard physics, galaxies should not be able to exceed certain velocity limits without external forces acting upon them. If some ultrafast galaxies are moving beyond these expected thresholds, it could suggest the presence of an unknown force or even a modification of general relativity that applies on the scale of galaxy clusters and beyond. If confirmed, this could revolutionize our understanding of gravity and possibly lead to a new theory that unifies relativity with quantum mechanics. Some physicists even speculate that hypervelocity galaxies might be linked to quantum effects on a cosmic scale. While quantum mechanics typically governs subatomic particles, some models suggest that quantum entanglement or other non-local effects might influence galactic motion under specific conditions. If high-speed galaxies exhibit unexpected correlations in their movement,